Hello, 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 hello.
Very good morning to all of you. I am Shivani Valecha, research scholar in the Department of Mathematics IIT Bhilai. On this auspicious day, we all are gathered here to celebrate the 134th birth anniversary of Indian mathematician Sri Srinivas Ramanujan as National Mathematics Day. We all are well aware of the extraordinary contributions made by Srinivas Ramanujan in the field of mathematics. So, to pay tribute to Ramanujan's indistinguishable achievements, the Government of India declared 22nd December as National Mathematics Day in year 2012. With these remarks, I would like to invite Professor Rajat Muna, the Director of IIT Bhilai, our invited speakers, Professor S. Punnuswamy, Professor in Department of Mathematics, IIT Madras, Professor Neeraj Mishra, Professor in Department of Mathematics and Statistics, IIT Kanpur. Professor P.D. Srivastav, Head of Department of Mathematics, IIT Bhilai, and our special guest, Mrs. Rajni Muna, to come up on the stage and kindly take the seats on the dais. I cordially acknowledge the presence of our invited speaker, Professor Anupam Sekia, Professor in Department of Mathematics, IIT Guwahati. Let us start this event by our customary lamp lighting ceremony. For this, may I now request Professor Rajat Muna, Professor S. Punnuswamy, Professor Neeraj Mishra, and Professor P.D. Srivastav and Mrs. Rajni Muna for lighting lamps on the stage. I would now request Mr. Milan Barik to welcome our esteemed guest by giving flowers as token of gratitude to them. Let us welcome the chief guest of today's program, our respected director, Sir Professor Rajat Muna. I would now request Mr. Milan Barik to welcome our invited speaker, Professor S. Punnuswamy, and present him a floral bouquet. Let us welcome our next speaker, Professor Neeraj Mishra. I request Milan Barik to present Professor Neeraj Mishra a floral bouquet. Let us welcome our next speaker, Professor Anupam Sekia. He has joined us online. He will be joining us online via teleconferencing mode. Let us welcome our special guest, Mrs. Rajni Muna. I request Mr. Milan Barik to present her a floral bouquet. Let us welcome the head of the Department of Mathematics, Professor P.D. Srivastav. I request Mr. Milan Barik to welcome Professor P.D. Srivastav with flowers. Thank you, Milan. May I now request Professor P.D. Srivastav, Head of the Department of Mathematics, IIT Bhilai, to address the gathering by speaking few words about today's program.
So, good morning to all of you. And on behalf of the department and on my own behalf, I welcome you all. I welcome Professor Muna, Chief Guest and the Director of the IIT Bhilai, Professor Punnu Swami, Professor of Mathematics, IIT Chennai, Professor Neeraj Mishra, Professor of Mathematics, IIT Kanpur, Professor Anupam Sekhia, Professor of Mathematics, IIT Guwahati, Mrs. Rajni Muna, Program Coordinators, my colleague, faculty of the other colleges, and dear students. It is my great pleasure to welcome you all on National Mathematics Day 2021, organized by the Department of Mathematics, IIT Bhilai. India has given a lot to the world of mathematics right from the initial days. For example, Aryabhat gave the world of mathematics the digit 0. When Indian mathematicians, say Brahmagupta, Srinivas Ramanujam, and others were ruling the world of mathematics. Today, we are celebrating National Mathematics Day 2020-21 in the honor of 134th birth anniversary of famous Indian mathematician Srinivas Ramanujam. The basic aim of celebrating such a day is to foster scientific temperament among the youth and encourage them to take baby steps in the world of mathematics and explore its applications in the spheres of economics, science, and other disciplines. Srinivas Ramanujam was born in the year 1887 and died in the year 1920. During this short period, he compiled nearly 3,900 results, mostly identities and equations, on his own without any assistance. Many of the results were completely original and novel, such as the Ramanujan primes, the Ramanujan theta function, partition formula, and mock theta function. These results and identities have opened entirely new fields of work and inspired further research. Apart from these, Ramanujan came out with his own theory of divergence series. Ramanujan worked on the Riemann series, the elliptic integrals, hypergeometric series, and the functional equations of the zeta function. Along with British mathematician Hardy, Ramanujan has discovered the smallest number, 1729, which can be represented as sum of the two cubes, and later it is known as Hardy-Ramanujan number. Now, with these words, I once again welcome you all on Indian Mathematics Day 2020-21 and wish that lectures and quizzes will definitely benefit you. And with all, thank you very much, and once again, bye.
Thank you, sir, for your kind words. May I now request Professor Rajat Muna, Director IIT Bhilai, for the welcome address of today's program.
Thank you. And good morning to all of you. So today we are here, Professor P.D. Srivastav from Department of Mathematics at IIT Bhilai, head of the mathematics department. Professor Neeraj Mishra from Department of Mathematics and Statistics from IIT Kanpur, and Professor Pannuswamy from Department of Mathematics, IIT Madras. All those who are present here. National Mathematics Day is a very interesting day to honor or to recognize the mathematical contributions and give certain kind of push for the knowledge of mathematics, right? To bring excitement about mathematics. And as Professor P.D. Srivastava talked about, Ramanujan, who was one of the greatest mathematicians of modern time, right? He was born in Tamil Nadu in a very small family, but he was recognized as a prodigy even in his school days. And later on, when he actually went on to do his research with Hardy, there are so many stories that actually come about. First of all, it was said that he, like in any Indian system, normally we don't follow a structured way of doing certain things, right? So a structured way of theorem proving and these kind of things. Of course, modern mathematics has brought in, at least in the school days, but that was not the case when early mathematics was there. And Ramanujan was a man with whom numbers were like trivial thing. Numbers were his friends. So the numbers will just float in his eyes. Okay. And one of these days when he was invited for dinner, he went by a taxi and he just told that I came by a taxi, which is a very interesting number, which can be represented as sum of two cubes in two different ways. And that's how, so Hardy actually asked him, and he said, this is the smallest such number. So Hardy actually asked him, how did you do this? How did you figure it out? And you just come 20 minutes into this cab, and how did you figure it out? And his answer was, no, it's just that it just came to my mind. God just gave it to me. It just came to my mind, and then I just calculated or whatever. Later, they actually worked on that, and they find these Ramanujan Hardy numbers. Of course, now we have many such numbers known, because of computations and all that. But I think this is something that Indian mathematicians, right from the early era, has actually contributed a lot to the mathematics, whether it is planetary astronomy, right? And people actually knew, the Indian astrology system actually talks a lot about, when you are born, what was the planetary situation, what was the planetary position. And these are all empirical formulas that over the years have grown basically by, Indian mathematicians, big names. And even today, that system is prevalent, right? When we actually go and when somebody is born, people go and get the planetary motions or Janampati, what is called. And Indian system was always to record important events using astronomical situations. What was the condition, at that point in time, what was the alignment of, various planets and stars and all that. So this actually has been a very, very interesting way of recording various historical events. The literature is full of these things. When did, for example, when did Raja Harshvardhan, when did his Rajyotsav or Raj Tilak happen and all that, or these are like recorded histories, and this is much better known, that this is the time when it happened. But I think very important thing is that Indians were well aware of numbers right from the beginning. Professor Srivastava talked about that Indians gave zero. Okay. But apart from zero, there are many other numbers that Indians gave. And one of this research that a lot of people have done is knowing of infinity. Infinity is one very interesting number. In today, it is actually being taught in the schools, colleges, and all that. What is infinity? But infinity is not a very simple phenomena. It's a very, very complex phenomena because you can't say what is infinity into 5 or what is infinity into 0 or what is there. There's so many undefined numbers that come in and then they actually get defined in certain contexts. So there are various things, but then the Indians actually knew large numbers. And it is recorded that, we know हजार, 10,000, lakh, 10 lakh, crore, 10 crore, and all that. That, of course, everybody knows. But then, if you actually go by this, Kharab, 10 kharab, Padma, 10 Padma, Mahapadma, and all that. So, people have actually worked out and they could actually go to as much as 10 to the power 243. Now, that's the number which is actually recorded in our Indian ancient literatures to say these are the numbers, these are the ways numbers could actually be taken. And this is, virtually it is all infinity, right? I mean, for almost all, purely if one says, 10 to the power 243 is not infinity, but virtually it is all infinity, as engineers would normally say, it's close enough to be infinity. So the man at that point in time knew in India what is infinity, and the education
Hello, hello.
Yeah, okay. Yeah. So my host actually, Professor Matthew Warinen, he was just began his work on what is called hypergeometric series, a topic which was also influenced greatly by Ramanujan. So when I applied for a postdoctoral position, he asked only one question: do you know about the Ramanujan's asymptotic formula for hypergeometric series? I said no. Then he said, that's the problem you are going to discuss when you arrive Helsinki. And so therefore, that's the reason, I decided to give a little importance about hypergeometric series at the very basic level. And probably some of you may not be knowing about the importance of hypergeometric series, at least those who are in the school, but I try my best to see that you appreciate the basic ideas behind the formulation of the questions related to hypergeometric series. So therefore, so you will see from my lecture on that aspects. So besides that, I would like to say that Ramanujan Mathematical Society is, organizing periodically conference. I think yearly conference is one, and then we support by providing resource person to organize small meeting workshops, both at school level and university level and higher level. So this has been going on around the last few years after I took over the in charge. I think every year we have been doing about 5-6, roughly in a year, 5-6 in a meetings in various parts of the country. So the next meeting is going to be in Punjab. So with that few words, I thank you all for coming forward to listen to this special day, the Ramanujam, National Mathematics Day. As everyone said, it's for the recognition of the great Indian mathematician. So with that few word, I look for your participation in the whole day affairs. Thank you. Yeah.
Thank you, sir, for your inspiring words. May I now request our invited speaker, Professor Niran Mishra, who is one of the distinguished researcher and professor in IIT Kanpur, to motivate the audience.
To be a speaker on a very special day, which happens to be the birthday of great mathematician Ramanujan. What I would say as a word of motivation to all of you is that if one mathematician, if you are given a choice to choose one mathematician to draw inspiration, I would say it should be Ramanujan. I don't think this world has ever produced a mathematician like Ramanujan, a person who did not have any formal training in mathematics, a dropout from college. He couldn't complete his bachelor's from Madras, University of Madras. But his fascination, his total devotion for the subject brought him to the limelight. And if you look at the short span in which the kind of mathematics, the kind of non-trivial mathematics which this great man has done, right? I think his birthday was 1887 or so around, and I think he lived hardly for 32 years. And within those 32 years, you look at a part of that went into finishing +2, going to college. And whatever mathematics he learned everything of his own through two books, right? Two elementary books which were proposed to him by somebody. And those books, if you look at, those books are still available on web. They look like your coaching notebooks, right? Which you see JE kind of a coaching notebooks, where a lot of formulas are there without proof. So all beautiful formulas, and Ramanujan made it a point to prove each and every of those formulas of his own. And he came up with his own proofs of those, many of those identities which are available in that book. That was the training which he received. So unlike most of you who go to schools, go to colleges, you learn about writing a theorem, right? How to write a proof of a theorem. He did not know. He did not have any training to write a proof of a theorem. Whatever he did with his own mind, right? Whatever he had his own ways of proving the theorems. So he did not have any formal mathematics training. And then look at the span in which he did that non-trivial mathematics. His first correspondence with Hardy was in 1913. So before 1930, he did not have any formal collaboration in mathematics. So he was doing everything of his own. And he died in 1920. He was infected with tuberculosis in 1918. So essentially 5 years of active collaboration, if you look at. And within those 5 years, without formal training in mathematics, of course, he had accumulated a lot of results before, but he did not have any formal way to get those results validated by a professional mathematician. And as a consequence, because he did not have any formal training, a lot of the results which he thought were correct turned out to be incorrect, because as such, I said he did not have a formal training to write down the proofs. And when he tried to approach some of the mathematicians in the West, the initial response was not very positive, but he did not give up until he came across with Hardy, who invited him to Cambridge, which must have been 1914 or so. So whatever he did with Hardy started in 1914, plus 5 years, 1919. Another 1 year is passed. So within those 5 years, just look at the kind of results which he brought to the notice of the rest of the world. So I would say that try to read something about Ramanujan, the kind of results which he initially thought were correct. And also it's important to read many of the results which he thought were correct, but later turned out to be incorrect. Because they also provide you a motivation to look at what may sometimes go into wrong if you're not doing a very sophisticated kind of a mathematics, right? Which you are fortunate enough to learn while doing your master's, bachelor's over here, which was not the case, as one of the speakers said, in those early years. So I wish you a very nice day today, and I see Professor Ponnuswamy is going to talk about Ramanujan works today. I'm sure that's going to be very motivating for all of you. So with these words, I just finished my short. Thank you very much.
Thank you, sir, for such an insightful speech. I would now like to thank all our esteemed delegates, faculty members, and participants of today's program. We are really obliged by the gracious presence of you all. I request Mr. Milan to present mementos to our esteemed guests as a token of remembrance. I request Mr. Milan to present memento to our chief guest, Professor Rajat Muna. I request Mr. Milan to present memento to our invited speaker, Professor S. Ponnuswamy. I again request Mr. Milan to present memento to our invited speaker, Professor Neeraj Mishra. I request Mr. Milan to present memento to our special guest, Mrs. Rajni Muna. I request Mr. Milan to present memento to our head of the Department of Mathematics, Professor P.D. Srivastav. With this, we come to an end of our inauguration session. We will now take a short tea break, after which our invited speaker, Professor S. Punnuswamy, will deliver the first talk of the day. I request you all to take refreshments arranged outside and join the program in this room after 10 minutes. Authors Award received by him in year 2002 for the book entitled Foundations of Complex Analysis, and C.L. Chandana Mathematics Award by the Canadian World Education Foundation. In year 2019, he has been elected as the president of Ramanujan Mathematical Society India. Along with this position, he also holds a position in various academies like Indian Academy of Mathematics, the National Academy of Sciences, and is a member of various committees like DST, FIST. The title of his today's talk is Ramanujan on Hypergeometric Series. May I now request Professor Punnuswamy for starting his talk? Yes. Sir, you can advance.
So once again, let me thank Professor P.D. Srivasu, the head of the department, and the colleagues who invited me to be here. And it has been a great pleasure for me to be here. It's the first visit to IIT Bhilai and even first visit to this region. Okay, good. So let me focus a few things on this topic, at least since there are young students. So let me brought out some information about Ramanujan. Of course, most of you must be knowing, but still some would be helpful for you. I mean, some of these already familiar, perhaps. But let me start with the basic quotes from Ramanujan. He says that an equation for me has no meaning unless it expresses through the what's called the name of God. So that's the kind of phrase Ramanujan used. Okay, right. Okay, yeah, good. So we know Ramanujan's born in 1887 and 1920 he died, and it's a true friend of numbers. So therefore this, okay, so what we are going to do here? We briefly, as I said, we briefly indicate about Ramanujan's early career, and then I'll begin to discuss some basic aspects of hypergeometric functions that Ramanujan began to just formulate many issues. Some of them are at the level to start with for school boys, and that's the first part. And the second part, I will emphasize a bit on not special function, but special function is actually is like a wild tree, but we would pick up only a small leaves from the class of special function, the hypergeometric series. Okay. Then I would indicate how the role of hypergeometric function, the topic influenced by Ramanujan, is still has impact to solve long-standing open problem. So at least I would give a couple of indication. So my interest on this topic is basically only for a few papers. When I visited Finland and my host asked me some question, I answered that question. It is trivial question, so I answered that question that's related to work of Ramanujan. So that's the day, I mean, that's the time I understood a bit about what Ramanujan used in terms of hypergeometric series. So when he asked me to give a talk, I thought that because it's a national day, so we should emphasize a bit the topic influenced by Ramanujan, and that's why I chosen. This is the first time I'm giving this kind of talk for the student level. Okay. Right. Okay. So therefore, my early life I will indicate, and then there is a question about perimeter of ellipse. Okay. I asked the students who are sitting on the dais. We know the perimeter of a circle, right? And then what is the perimeter of an ellipse? Do you know already? You have a compact form. There is exact form for a perimeter of a circle. Suppose you have a circle of radius r. So what is the perimeter? 2 pi r, and we know the area pi r squared. What is the perimeter of an ellipse? Do you have a compact form? Okay, let's see. Okay, so therefore Ramanujan, when in his early days, he started even looking at that kind of questions. We will see whether there is an exact form or not. What kind of exact form we know. Okay. So that's what at the students level. And then second part starts with, there is a famous conjecture. I think those who work in complex analysis, they must be knowing about the Bieberbach conjecture that was open for more than 70 years. But the solution to this conjecture after 17 years come from an identity that was placed in more general form by Ramanujan. Later, the special cases were used by a lot of people. This kind of identities become a special role in solving a long-standing open problem for 70 years. At least you don't worry about the technical part. At least you should know what is the problem and how hypergeometric series are used, what the special relationship between hypergeometric series, how it has been used to solve the problem. I just indicate. So I would avoid all kinds of technical parts. So therefore, you can, when you go out, you will understand, okay, this is the thing, this is the thing. At least when you want, you can browse through in the net. Okay. So lastly, not only that, so when you look at little more closely, how this topic is also related to function spaces, in other words, operator theory point of view, that's a topic influenced by Hardy. Okay. So I will just indicate that. Again, I avoid technical things. So lastly, the very important aspects of Ramanujan is to the asymptotic relations for hypergeometric series. That's where I just played a role. Okay. In fact, I would proud to say that when this question was asked from a paper which was published by 5 different people about a refined Ramanujan's asymptotic formula published in Transaction of American Math Society, and I was asked to comment on that paper. So I told them that all these results of this paper could be answered in a couple of pages. Then they surprised. This finished mathematics surprise. Then they raised the questions which was not addressed by Gauss and Ramanujan. And I said, okay, I can solve that problem. That was a paper that I solved very short span, which is a highly quoted paper among all papers. But I spent a lot of time in some conjectures. Many years I solved it, that was not quoted often. So that shows the importance of certain problem influenced by people like Ramanujan has impact in other areas. So therefore, so there is something you do for satisfaction, your own interest, something you do that attracts others. So Ramanujan actually, all his work, each and every topic, if you look at split into several categories of topics, you will see each topic gets influenced by many. So that's very important about Ramanujan's work. Okay. So therefore, that's the thing. And then there is a relationship between functional inequalities and modular equations. So I may not be able to touch. Okay. So good. So first part is about Ramanujan. So some of you already know. So first of all, you should remember about the 3 mantras. Okay. So one is how to develop your talent. If you have already developed a talent, how to use it. And you should know your potential. And then, you have to go next stage to achieve your goal. Okay. These mantras are well remembered by everyone. And so Ramanujan remembered in many ways this. Okay. Yes, as everyone knows that today is a 134th birth anniversary, which is celebrated as a National Mathematics Day. Okay, so this is Ramanujan was born in 1887, December 22nd, in Erode. I do not know how many people know about the city Erode. This is a city where there are many cotton industries, silk industries. Okay, and that's the city is between Chennai and Coimbatore. Okay, that's the place he born. His father was Srinivasa Iyengar. Okay, he was an accountant, and he was actually a city official. But still, people say the whole family lived in poverty, which I do not know. Okay, but anyhow, it is recorded anyhow. So he was attending the school at the age of 18, and there is a famous small town, Kumbakonam, is a city of temples. Kumbakonam is a city of temple. That's the place. There is a famous engineering institutions, Sastra University is there. That was set up some years ago. Okay, anyhow, so even at the young stage, he demonstrated the extraordinary proficiency in mathematics, but did not pay much attention to other subjects. But his extraordinary talent impressed very much, impressed his teachers very much and everyone else. Okay. At the age of 16, Ramanujan matriculated at the government college at Kumbakonam. So as I said, Kumbakonam is very popular for Hindu temples. Okay. But anyhow, he lost scholarship the next year because he did not pass other subjects. And somehow he spent all his time, his mind was all the time working in only one direction, not with other things. His thinking is only in mathematics, he failed. But this not, I mean, unfortunately or unfortunately, this did not disturb him to pay more attention to do more in mathematics. So that's, anyhow. So therefore, he failed in the, exams. He did not get a scholarship. But then, because of that, he needed to search for a job. Okay. Some battery problem. Someone. Okay, yeah. Okay, yeah. So what was the, in the early days, the only book he knows or he used is the book by Cars. And this is synopsis of elementary results in pure mathematics. This is the only book used, and this book contains more important aspects of integral calculus and then power series calculus. And in the early stage, his concentration is looking at the exercises and finding it very trivial from that book. And that book helped him to know what's going on in calculus. Besides that, he did not know what's going on in mathematics outside. Anyhow, so as Professor Neeraj pointed out, he worked independently on mathematics, writing down results in 2 notebooks without bothering about proof. Okay. But anyhow, so in 1909, he began publishing a work in the Journal of the Indian Math Society, which gained him a special recognition of his work. Okay. In spite of the fact that he doesn't have any formal university education. Okay. But as I said, he failed in other subjects, so he needed employment, so he became a clerk in 1912. But even in his office, in the book, you will see, even in his office, he all the time, he works only mathematics. He finishes the regular routine clerical work, and then he writes a lot of formulas, new identities, many more. Yeah. So that gave him more recognition. But everybody knows that now he lived only for 32 years. But the wonderful book, which I think now it's available in most of the Indian languages, The Man Who Knew Infinity. And the Hindi version of that is going to come up maybe very soon, next year or so. But otherwise, it's there in most of the Indian languages as of now. Okay, so I think, how many of you seen this film about Ramanujan? Most of you? Yeah, very good. Yeah, very good. So there's also a film about Ramanujan, which was first premiered at the 2015 Toronto International Film Festival. But most interesting aspect is that Bruce spent his whole lifetime in looking at all aspects of the work of Ramanujan. So he brought 15 books to his credit, out of which 10 books are related to Ramanujan's work. So that's a very solid thing which no Indian have contributed towards that. Well, he made substantial contributions to mathematics, including results in number theory, analysis, as I said, more importantly, infinite series and hypergeometric series 1, okay, without formal education. Okay, so this also the fact that already has been explained. English mathematics Hardy had received a strange letter from Srinivasa Ramanujan. So that letter was 10-page letter, contained only about statement of theorems without proof. So nothing else, just a statement of proofs, and mostly on infinite series and something related to integrals, something related to what is called the continuity fractions. Of course, there are many related stuff about number theory. Okay, so some of them generated some discussion between Hardy and Littlewood. These two are a giant in Cambridge or British group of mathematics. So Hardy showed the letter of Srinivas Ramanujan to his collaborator Littlewood. They are very pioneering work in that period. So after a few hours, they concluded that the results must be true, because if they were not true, no one would have got that strength to imagine for that kind of invention. So they come to a conclusion that he must be very genius. Okay, so therefore Hardy immediately began to arrange his visit to London, UK, and then there was some, the typical Tamil Brahmins, they are not supposed to travel by overseas. Okay, so therefore Ramanuja was not interested to fly, or to, sorry, not fly, those days no flight. So he does not, he didn't take interest to travel by ship because it has to cross the sea. But his mother indicated, no, you should go, because I dreamt that the goddess of, the Namakkal. Namakkal is a famous temple. There is a famous Hanuman temple there. So the Namakkal goddess, informed me that I should not prevent Ramanujam going to England. So that made him kind of encouraging from his mother. So then he decided to travel to UK, and then of course that helped him to get the collaboration further with Hardy and many others. Okay. So Cambridge University granted Ramanujan's bachelor degree by research in 1916. His thesis was based on highly composite numbers. As I said, numbers were a good friend of Ramanujan. So that's the first thing. Okay. Then later in 1918, he was elected the Fellow of the Royal Society. He is the second Indian to be elected. The first Indian was from somewhere from Maharashtra. I don't remember his name right now. I noted, I forgot, but that was for a shipping related investigation. Okay. He was the first Indian, and who made a lot of contribution how to make ships. That's the first thing. Okay. And then he was the first fellow, Indian fellow, who was honored by the Trinity College as a fellow. So that's the yearly recognition for Ramanujan. Okay, right. So in his journey, so remember in 1917, I think this was also pointed by Dr. Neeraj. So Ramanujan became seriously ill, so possibly from tuberculosis, and was admitted to a nursing home at Cambridge, and then moving to different nursing homes as he tried to regain his health, but was not successful. But then 1919, he showed some recovery and decided to return to India. But during that period also, he wrote a lot of formulas, identities without proof. Okay, they were the part of Ramanujan's last notebook. Okay, then he died in the following year. So one of the remarkable results about Ramanujan, the Hardy-Ramanujan collaboration, was exactly the number of partition for a given integer, positive integer. The partition of a positive n is just an expression n as a sum of positive integers in many different ways. And the question was to derive an asymptotic formula because for a large number, you cannot really count how many ways one can represent such a number in different ways. So therefore, this is the quickly derivable by Ramanujan, but difficult to understand unless you know about all these deeper things. Okay. Okay, there are many such things. I will at least point out. I will point out some more. Yeah. Okay, now the Fermat's last theorem, you remember now. I think it has been now known. Okay, so look at the three possible. Look for three possible integer solution of this relation of n equal to 2 is your Pythagoras theorem. That's well known. But for n bigger than 2, there is no integer solution. But then question is, are there an integer solution near to integer solution? So that's what the Ramanujan looked at, even this, without much knowledge about Fermat's conjecture. Okay. Anyhow, so the question is about, there are finally Andrew Wiles proved this. There are no positive integers, A, B, C. We can satisfy this equation for any n bigger than 2. But before that, this number is now already known. There already in the entrance of the hall, and the taxi cab number, you know, they were going on a taxi, and in a conversation, Ramanujam asked Hardy the number of the taxi he had traveled in. Hardy replied, "Oh, it's dull number." And Ramanujam, no, it's a fantastic number because that number is actually very interesting number for reasons above. That means this is the smallest number that can be expressible as a sum of cube numbers in two different ways. Okay. Now look at this, these two 10 cube and 9 cube. Roughly, the sum is actually 1728, which is actually 12 to the power cube. But now it looks like it gives a solution to, you know, the previous Fermat's questions. But if you add 1, so the 1 is the missing number. So therefore, so it is natural to look at, to identify, to generate whether this has a solution, but not the Fermat's. Answer is yes. Okay, so how we have a small addition or small subtraction. That means that subtraction of a 1 and addition of a 1 leads to interesting solution. For example, well, so therefore Ramanujam identified this, and he find a way to generate an infinite number of near missing equation of this form. So this form is coming from Fermat's theorem. See how he looked at the problem. Okay, so when I looked at the plus or minus 1, remember this, that's I am going to use in hypergeometric series. Okay, so you, yeah, for example, I have given few simple expressions where see that this is minus 1 is required, and in this case, for example, minus 1 is required. If minus 1 is not there, it would have been a solution for Fermat's last theorem, but it's not true. But by adding minus 1, well, the identity holds. So therefore, this is simply a near missing solution of the Fermat's last theorem, for example. Okay, so this is not the only thing. These are just few simple cases I have indicated. Okay, then Ramanujam. Okay, I want to indicate this also. What we have done for Ramanujam. Of course, in 1997, the Ramanujam journal published by Springer was launched, and this is mainly to cover the areas influenced by Ramanujam. And so this was launched in 1997. In order to popularize the journal the very early days, I was also invited to give a contribute article on the work of Ramanujam, since I was working on that topic that period in Helsinki, University of Helsinki. So the journal was popularized with a few issues in the beginning, where I also wrote some articles about Ramanujam's influence on hypergeometric series. So then after, I did not do much work on hypergeometric series, I should say. Okay, so of course, RMS, Ramanujam Math Society, which has its name, Srinivas Ramanujan, was founded in 1985 at Tiruchirappalli. Tiruchirappalli is again a place for famous for rock temple, and famous for another temple, Srirangam. Okay, and then close by Tanjore, 40 kilometers, there's a famous solar temple, and then another 50 kilometers, Kumbakonam, the place of Ramanujam, where he went for schooling. Okay, so his hometown now, his home has been converted to a museum that has been set up by the Shastra University, which is in Tanjore. Okay, so this is about a little about Ramanujan's early things. Okay, now let's go to the second part of this lecture, which might be of interest to you. Suppose you look at a smooth curve. Okay, for example, if you have a circle, you know how to find the length of the curve. Okay, there's an interesting formula which is also available in basic book. If you have a complex and if you want length in terms of parameterized curve in the complex plane, this formula will become modulus of z primes, modulus of z prime into dt. So it's all same, either form. Anyhow, so you know this formula very well. So now when you use this formula, and if you have an ellipse with the semi-major axis A and semi-minor axis B, so then you have a parameterized curve for the ellipse, A cosine theta and B sine theta, plug them inside, and then you can write down an equivalent form of the length of the perimeter of the ellipse. Okay. Okay, so by doing that thing, okay, but of course, all these basic things known for you. For a rectangle, you know area, you know the perimeter. For a square, you know the area, you know the perimeter. For a rectangle, you know the perimeter and you know the area. For example, the circle, you know the area, you know the perimeter, and for in a parallelogram, you know this. But for ellipse, see here you see the perimeter is in a compact form, you see the area is in compact form. The question is whether the ellipse has a compact form or arc length or completely the perimeter, full perimeter. Arc length is just a part of it. Okay. Yes, so therefore you know the notion of what is the eccentricity, assuming that A is bigger than B. Okay, when A equal to B, then it's actually circle. Okay. So therefore, you assume E is between 0 and 1. Okay. So let's denote the perimeter of the ellipse, some P of A comma B, or simply by P for a convenient. And the question is, we know the formula for the length, and then use the parameterized form. You will end up with the explicit some form involving integral. Let's not worry about that. See, this P is your perimeter. Look at a circle of radius A. Assuming that A is big, so therefore this is so this gives a kind of upper bound for the perimeter, first of all. So this area of the circle is 2 pi A, so it cannot go more than that. Well, so now here to here it is 2A, and when you go around this, then it is the lower bound has to be 4A. So when you make this smaller and smaller, you will see at least that way. So anyhow, so at least it's 4A, at most it cannot be this. So this is the bound for the perimeter of an ellipse. Okay, good. So this is intuitively very, geometrically it's very clear. Okay, right. So when you use the parameterized form, you will get exactly this form. Okay. You will get exactly this form where E is actually this one, and this integral is called complete elliptic integrals of the second kind. The word elliptic is coming because this expression coming from determining from the formula for the perimeter of an ellipse. So 4A times E of E. So that means this. Okay, so look at this one. This function is clearly a decreasing function of x. So therefore, you know, this E of x, this value should be lesser than E of 0 and E of 1. And you see that this is, and then you can see that P is again this. So earlier what we saw was actually, it was using geometry. Here it was using analysis. By using the analysis, that means the integrand is a decreasing function of x. So that therefore this is a positive integrand which is decreasing. So the upper bound should be evaluated at E of at 0. That's what E of 0, and at 1, and that's what actually evaluate 1. So therefore you will get 4A times these two numbers, and that's okay. Right. This is very light. Very simple, and that okay, but are there a simple exact formula ellipse? The answer is actually no. Unfortunately, unlike the case of other pictures like circle, rectangle, parallelogram, we do not have a very simple form. So there are simple formulas, but they are not exact. But there are exact formulas, but they are not so simple because of the following reason we are going to explain. Okay, the first exact formula of ellipse was presented more than 200 years ago by Maclaurin. That was actually converting the integral into an integral into a sum. Into sum means, you know, the series form. So it is just term by term differentiation of that integral by separating the square root in terms of a formal, binomial series expansion. So integrate term by term using the information about integral of sine power n times x, something like that. So you will end up with this formula. Yes, remember that except for k equals 0, rest will be negative. When k equal to 0, this is 2 pi a because the whole thing is 1. So 2 pi is the leading term. And other than k equals 0, all will be negative. So therefore, this 2 pi a is actually is the upper bound. So that's also clear from this expression. Okay, do you understand that? Well, see, this original series actually, as I said, it originated from the expression for E of x. And the next identity is due to, Ivory in 1796. These two are, of course, same. I mean, it is like transferring some way this summation into this summation. How do you transfer? So, and he transferred in, some reparametrizing the integral by change of variables. Okay, but actually the hypergeometric series play a role. I will explain about that later. So therefore, so you want to know what is the relationship. Later we will see that what is the relationship between A, B, C. I explain what are these things. So relationship between this and then this plus or minus 1, B plus or minus 1, C plus or minus 1. Sometimes this may not occur. Okay, if you use Z as a variable, then you should. So essentially, there are nice contiguous relationship between hypergeometric series that I will explain later, and that's where this plus or minus the missing parameter in some way. Okay, so now what we have seen, this is simply expressing the original integral into series form by using binomial expansion for the which is inside the integral. So then term by term integration leads to this is obtained in some way using a change of variable. That change of variable kind of things helps to generate identities involving the hypergeometric. That's I come back to that a little bit. Okay, anyhow, so what do you mean by hypergeometric series? It is simply a series of this form. For example, say when a equal to 1, b equal to 1, c equal to 1, all these coefficients, so you must remember this notation, which is ascending factorial notation. So this is a into a plus 1. It goes all the way up to a plus n minus 1. Okay. So for example, if you have 1 comma n, you remember this 1, 2, 3, 4, etc. up to n. So therefore, this becomes n factorial. So if you look at 2 comma n, so you remember 2, 3, 4 up to, when you put 2, you have n plus 1. So it has n plus 1 factorial. So remember that. So when all these ones are, all this parameter assumes the value 1, then the coefficients is going to be 1. It's actually the series. Okay, so therefore I am not going to use much specific functions. At least you must know this series. This is geometric series. Okay, k equal to 0 to infinity. Okay, z power n. So next one is, you can obtain by differentiation, but you need to convince why differentiating this is same as differentiating term by term. That's different story, but that's also same as putting some specific value for a, b, c. Okay, so this will be something like this is n. So n equal to 0 to infinity. If you want to multiply by z for convenience, so this becomes n into z power n. I'll come back why this function is very important in posing some conjecture. Okay. Anyhow, so I give you a little bit about what do you mean by hypergeometric. It is simply a series where these coefficients, if you look at this coefficient as an, there's a Taylor coefficient. Okay. If you look at an plus rational number. So one way to define hypergeometric series is by saying that the coefficient of the hypergeometric series an plus 1 by an is a rational. So that's one way to begin with. Anyhow, so in these years, the perimeter of the ellipse has been given in terms of only the hypergeometric series with specific values at a, b, c here, a, b, c, and this number delta is defined here, and then this h is defined here, and all this simple trusting in terms of change of variables help to understand how the relationship between hypergeometric series with the change of sign plus or minus 1 helps to generate identities which are useful in many sense. So that part only I'm going to cover. So I don't want to any technical things. Okay, so there are several such nice identities which helps to solve many problems, and that's the reason I said. So here what I want to say, these are the year, in these years, the perimeter of the ellipse has been given in the form of hypergeometric series, which has no compact form. So therefore, one expect a simple approximate value of this, which gives you close enough to the value of this hypergeometric series. Okay, and that is the problem that Ramanujan paid attention, that attracted later. Even today also, there's a paper a few years ago dealing with the relationship, the asymptotic relation determined by Ramanujan in connection with the perimeter of the ellipse. Okay, so although Ramanujan, idea was to just look at one, or one or two good approximation of perimeter of the ellipse, but the idea that he generates help to build many more things. Just that's what very important about the Ramanujan's work. Okay, good. Okay, so this is a very known fact. Okay, the good approximation how people do when a equal to b, this is 2 pi a. So therefore, perimeter of ellipse roughly 2 pi a. That's very simple approximation. Of course, here also when you take a equal to b, this is 2, then it becomes 4a square, 2a. It is actually again close to. So therefore, using the information about the perimeter of a circle, they want to give an approximation with respect to these two parameters a and b, with semi-major and semi-minor axis. So these are simple asymptotic formulas, which is nowhere close to a good approximation. So therefore, Ramanujan brought out these two formulas. How did he bring out these two formulas? When they were not much, knowledge about advanced tools, he brought such an approximation. Okay, well, these two approximations are very good in the sense, I'll explain later how many the error, they want to make the error term so minimum. They wanted to make the error term so minimum, and that's the way these approximations are uptight. Okay, right. Let's look at in this connection. In 1883, there was a good approximation of this. Left hand side is simply the length of the perimeter of the ellipse. Okay, which is developed with a simple function here. When you pull a outside, you can eliminate 2 pi a, and then you get 1 plus b over a, and that when you convert in terms of functions of x, it will look like this. So therefore, I call E as x, and then when you transfer this, so it is like this. So the question is whether this hypergeometric series is bigger than this or not. So this means we are looking at the lower bound for a perimeter of an ellipse. So having said that, so this is this a good approximation for perimeter of the ellipse? The answer is yes, it's a good approximation in terms of lower bound. So then we look for the higher bound. Okay, then the difference should be small. Then of course you have got a good approximation. Okay, so this was posed, but then in 2000, the Roger Barnard and a few others has raised the question. They look at a power series carefully. So look at this power series, expansion of h of x, except the first term remain in terms are negative. Here also you can look at that way. And then you look at the coefficient here as an and here as bn. The question is whether these coefficients are comparable. If this coefficient comparable, this is a more stronger result. This more stronger result. The answer is yes. Okay. Answer is yes. Okay, see that formula represented by a this hypergeometric series will reduces to that, certainly, yes. Because when a equal to b, what happened? These two, the numerator parameter is same, and then we have to fix c, and then how they went, and you rewrite this sum into compact form, you will get it that. Yeah, so that's an easy part. Yeah, anyway, yeah, it's coming. Yeah. Okay, so this is not a question just recent, but this is a question for long time question to find good approximation for the perimeter of an ellipse. Okay, so what is interesting about Ramanujan's approximation is that it is an externally unusual and exact approximation in the sense, if you look at the first 6 terms of the first Ramanujan approximation, that's a good approximation. And second formula is, when you look at up to the term involving e power 18 in this expression, so it's 9 plus 1, 10 terms. So when you look at the difference between the original and this, they are very close enough. So that's the interesting fact about Ramanujan. But if you want more information about how many such formulas, good approximations developed by people from different topics using different methodology, you can find from this link. Okay. Anyhow, so the Gauss developed a very efficient convergent method using what is called arithmetic and geometric means approach to get a good approximation of elliptic form. Okay. So the second part now, that's what we are going to touch. It could be slightly advanced, but I would rather say that just look at the definition of hypergeometric series. This is a series whose sum is represented by this function. Okay, forget about this analyticity and analytic continuation and all. Just it's a power series which converges in the unities, in particular as a function of real variable. It converges in the interval -1 to 1. Okay, think of this as a real integral, a real sum, and that means x power n, and x lies between -1 to 1. Okay, good. So this is just to indicate this series converges only in the interval -1 to 1. That's all. First. Okay. Well, then by replacing this one of the terms, the last one z by b, and then take b goes to infinity, this leads to another nice power series, and that power series converges everywhere. So it's like an entire function, and that also has a similar studies in the in deriving lot of identities. So that's just to indicate that. Okay, good. Now in the special case, what is interesting is there are some special cases where you can actually write down explicit form like this. For example, when the c equal to b, one parameter gets cancelled and numerator will have only one. Numerator will have, so if you know this formula for hypergeometric series, for example, you have f, a, b, c, z, and you have this, let me write down here. So a sub n, b sub n, this is c sub n, 1 sub n, and then z power n. Okay, so when b and c are equal, this goes off. Only it involves a and 1, and that has a very compact form, for example, some compact form like this. These are the functions you are already familiar for you. For example, when you take a equal to half, b equal to half, c equal to 1 by 3, of course, for convenient, I replace z by z square, then you get arc sine. That arc sine is sine inverse of x, for example. You have in a compact form. So when you take some other parameter values, you get the value, you get the explicit form. So there are some parameter values for which one can get explicit representation. That means the sum of this power series is compact, is exactly simple form, in other words. There are two cases where it does not yield. So this case is the, in that one involves the elliptic integral, the second kind, which is involved in the length of the curve, that means the perimeter of the ellipse, and this is called the complete elliptic integrals of the first kind. It is the k of z that has very efficient way of determining how far you are away from what's called the conformal maps. It's a big quasi-conformal theory which connects Teichmüller space and string theory where this function is involved so much. Okay, I don't want to get back to that. But anyhow, there is a book about hypergeometric series and special function more generally. There are 3-volume books which list, so hundreds of, rational triplets and the corresponding this one in a compact form. It's not just only few values of A, B, C, it gives you compact form. There are hundreds of such values. By choosing A, B, C, some rational triplets, and then you can get a compact form. In fact, if you look at the Wolfram Functions homepage, you will see out of 300,000 formulas, 200,000 involves with hypergeometric series. And this is brought out recently by a topic which was influenced by Ramanujam, centuries ago. So therefore, without realizing this is going to be this much use, he realized its importance. So that's there's another aspects of how one view the long-term effect of what you do. Okay, right. So now this is one thing that I would like to emphasize. This is a little bit advanced, I know, but I would like to emphasize this. Here is a function represented by a power series. There is a Taylor coefficients. There is a question about if this power series represented by the sum f, if it is 1, 1, 1, 1 mapping of some simply connected domain, and then there is a restriction of the coefficients, the Taylor coefficient an, and yeah, I think come. Okay. So I take another 5-10 minutes and then wind up. Yes, okay. Yes, so therefore the question about a necessary condition for a function to be 1, 1. Very question is very simple. It's a Bieberbach in 1816. He forced this conjecture, posed this problem. What he did is he did not pose this problem in the text. He, as a footnote, he mentioned this, perhaps this is true with equality for this function. That's what I mentioned. The n appears here. The very simple examples helps to build conjecture. And once they build the conjecture, it attracts some minds, and then they develop the theory. It took 70 years to get a solution to this problem. During the 70 years, people have developed different tools, different methods to find a way to solve this problem. When they are not able to find a solution, they try to develop something else through which, and that has developed the whole theory of what's called geometric function theory, okay, in complex analysis. Okay, finally, this problem received its solution, and this conjecture was solved. And this was done by somebody from Purdue University. His name is D. Branches. Okay, people did not believe that D. Branches actually solved this problem. Why? Because D. Branches claimed a proof of few conjectures before that. One of them was the Fermat's last theorem. The other one was actually Riemann hypothesis. All the time, people did not believe that he has solved this problem. So he was forced to check whether this is whether the proof he developed for this as a solution to this conjecture, he was forced to check from somewhere else who are familiar with this problem. Then he traveled to Russia, the St. Petersburg University now. It was before Leningrad University. He went with a 120-page proof of this conjecture. He went to that school and then they developed contact with the Russian mathematician, and then they tried to check the proof. They brought down the proof into 20 pages. Then it was accepted by Russian mathematician. After that, this paper was accepted and the solution was obtained. Solution obtained was correct, and this conjecture was solved. And then this person was not actually working specifically on complex analysis. He works in what is called summability theory. So he looks at the problem in different angle using some ideas from differential equations, some ideas from Ramanujan's identity of this type. Ramanujan actually posed a more general identity than this that has been used by Andrews, and that has been used by many other special function theorists. So what I mean to say, although this kind of identities were proposed or discussed about 100 years ago, this is still gives a key to solve hard problems. One of them is this. And this person, I am the second foreign mathematician went to that University, Petersburg. They showed me the table where they checked the proof, in Petersburg. Okay, so that's one thing. Okay, so now I come to a conclusion quickly. So whenever we look at any functions in a more general form, then one has to look at whether such a 2-parameter family of functions or 3-parameter family of functions, doesn't matter, whether there is a differential equation satisfy that. So because a differential equation often gives you much more information than some other form. So therefore, this is called the hypergeometric differential equation. And then one of the solutions of this one is the one I mentioned as a Gaussian hypergeometric series. Okay. So then, there are many questions related to that. Okay, of course, here I have a picture to give this 3 is 1 plus 2, 3 is 1 plus 2. I draw the picture for this function when c equal to 1, a plus b. That's called a zero balanced hypergeometric series. When the third parameter is equal to the sum of the previous 2 parameters, then this hypergeometry is called zero balanced hypergeometric series. That attracts the attention of Ramanujan for many reasons. I'll come back to the next slides. Forget about other pictures. Okay, so these are okay. Forget about that. Okay, this problem. Okay, I'll go back to Okay, yes, So it's an amazing result by Gauss that when the asymptotic formula as z goes to 1 for the hypergeometric series, which is zero balance, is actually minus log 1 minus z. That means the behavior of hypergeometric series is logarithmic. Of course, this is a constant here involved. Here, at some point, for some condition, you have an explicit form. Okay, then c less than a plus b. Of course, this is also known. These are very well-known results from Gauss, considered to be a great specialist in England. And Ramanujan looked at that without knowing much information about what has been developed before. And he proved a refined formulation of Gauss result that becomes, different of research for a different setting. So that means this b times this hypergeometric series, zero balanced, plus log, it's not only you can write down, you can explicitly look at this estimate for the error term. Here R is actually a number which is given in terms of this. Here gamma is actually Euler constant. So here another interesting question, which is actually calculus question. So gamma is a number defined in terms of limit of this. Whether gamma is rational or irrational is still an open question. Whether the Euler's constant defined by this is actually a rational or irrational is still unknown, still a unsolved problem. So there's a question about rationality of or irrationality of gamma is open. Okay, this is another thing. The question was, this was the question I was asked by Finnish mathematician. Okay, can you find a similar asymptotic relation for a non-zero balanced hypergeometric series that's for c lesser than or equal to a plus b? So that was actually not done by Ramanujan or by other Gauss mathematician, because they did not realize its use that time. But say those who work later stage, especially Vorinen and his group, when they started working on it, they raised this question. I answered this question, and that helped to many people to work on this topic later after the proof of this estimate for the error term. Okay, the first investigation was done by Ramanujan. That's meant for zero balanced, but for the non-zero balanced case, except Gauss, the explicit, some kind of error estimate was not known. Okay. Anyhow, so that was the precise information. During the process, we also refined Ramanujan's work. So this function actually lies in, by these two functions. One is a constant function defined by Ramanujan. So the other one is given by R plus that. So therefore, now it gives you good estimate for the error term by this expression. Okay, for C equal to A plus B, this quotient has some nice property. That's the interesting fact. But what is interesting is the following result. If you want to know, this is a basic calculus. If you want to know, suppose assume that denominator is non-zero. Okay, I want to know whether the quotient is increasing or decreasing, especially assuming that F and G has a power series expansion with Taylor coefficients non-negative. So you are looking at the quotient of two power series whose Taylor coefficients are non-negative. Question is, can we describe in terms of coefficients whether the F is decreasing or increasing? It is actually, that's the main result of this. Okay, if you have AN as the corresponding Taylor coefficient, BN is the corresponding Taylor coefficients. If AN and BN is increasing, then the function is increasing. If A and Bn is the quotient A and Bn is decreasing as a function of n, then the function is actually decreasing. So this is the key ingredient to determine this asymptotic formula, and that's what this. Okay, I think there are many other interesting information. So Ramanujan also derived how the quotient of hypergeometric series and its derivative as a compact form. That's another field where Ramanujan, pushed many people to think about its connection with elliptic equations and what's called the modular equations. Okay, so there's another area where Ramanujan posed many interesting theorems, statements, conjectures, solutions, everything. And myself and Professor Balasubramaniam solved such conjectures, couple of such conjectures. This was my early days work anyhow. Okay, and it was actually Bhargava and Bruce Bond. They made a long paper that's dealing with Ramanujan's theory of elliptic functions to different level. It's a long paper which contains nice identities involving theta functions and modular equations. So the Ramanujan's work in different areas of analysis helped many people to think more and develop many more ideas for others to work, think, and so on. Okay, so this is a quotient of hypergeometric series. Ramanujan also looked at the product of two hypergeometric series, whether hypergeometric or not. So we've already seen one example, square of hypergeometric series is actually another hypergeometric series. So therefore, a natural question, I'll just, one more line. Okay, I skipped that part maybe. Yeah, okay, yeah. So this is a student level, it should be interesting. So the power series form of this one. Look at the product of two hypergeometric series, a simple product, and this is true. And compare the coefficient of z power n on both sides. So this is just a Cauchy product. So you will have this coefficient of z power n, and then bring down to this side, so you get the average. Now you place this average with this, you've given a sequence of a complex number, a real constant, you pull them inside. So this is called the Sesarov mean. So the Sesarov mean, what has been looked at by people, Hardy and others, it's actually coming from product of two hypergeometric series become hypergeometric. Then you form a Sesarov operator by looking this as your Taylor coefficients. Now you look at this as a Taylor coefficient and formulate a power series, and then write down this in a compact form in an integral, and this integral becomes an operator. So therefore, many of the operatoric point of view of study also come very naturally by looking at the product of two hyperjump. And that's the reason the contiguous relationship between hypergeometry series with the plus or minus one variation helps to build many more things. Okay, so this is just a sense. For example, these relations. Look at this relation. Here is a b plus 1, here is a minus 1, here b plus 1, c plus 1, and these constants play the coordinate identity. So that's it. Okay, so that's all. I mean, so these are other areas where hypergeometric series play a key role in building a new technology, in the sense that new theory in the study of many different issues related to operators. Okay, so there are no more unless you have some question. Of course, second part, I know students have some reservations, but I just want to emphasize how they build, from the basic to little higher level. Yeah, thank you so much. Yeah.
Thank you, sir, for such an interesting talk on hypergeometric series and early life of Ramanujan. We all came to know that how several results by Ramanujan opened up the new vistas of research in mathematics. Now, I am immensely pleased to introduce our next speaker, Professor Neeraj Mishra. He is currently a professor in the Department of Mathematics, IIT Kanpur. Professor Mishra has received his doctoral degree from IIT Kanpur. He has varied research interests in theoretical and mathematical statistics and its applications. He is a recipient of various prestigious awards like Jacob Wolfowitz Award in 2003 by American Journal of Mathematical and Management Science, New York, and the Teaching Innovator Award in 2016 by MHRD. The title of his today's talk is Statistical Thinking. May I now request Professor Neeraj Mishra for starting his talk?
Okay, thanks. Nice introduction. So the topic which I have chosen to speak about today, as such, doesn't have direct relation to the work of great Ramanujan. But I would like to try to relate this work with Ramanujan's life in certain way. You see, while Ramanujan was visiting Cambridge, there was another great Indian mathematician, P.C. Mahalanobis, who was also visiting Cambridge. And while both of them were over there, they became friends. Mahalanobis, P.C. Mahalanobis, many of you may be familiar with the name. This is, yeah. Now, P.C. Mahalanobis is called the father of modern statistics in India, right? So whatever statistics which you see, incidentally, Indians have done very well in the subject statistics. And if one has to define father of all that, it is P.C. Mahalanobis. And while P.C. Mahalanobis was visiting Cambridge, Ramanujan was there. They became friends. And P.C. Mahalanobis, in one of his writings, has explained about the philosophical aspects of Ramanujan, which he claims that he could never understood because they were so deep. So it looks like there was another side of our Ramanujan which possibly went undiscovered, which was his philosophical side, and which he always claimed that he has some special relationship with the God. And so in a brief article, Mahalanobis mentions about those philosophical interactions with him. It would be interesting to read those. So one of the very anecdotes about this P.C. Mahalanobis' interaction with Ramanujan at Cambridge was, you see, when Ramanujan went from India to Cambridge, England is normally much colder than India. So Mahalanobis visited his apartment, and Ramanujan was shivering, right, with the cold. So then what Mahalanobis observed was he had a bed, and जैसा आप लोगों ने देखा होगा, if you go to the hotels or even if you go to these modest guest house these days, वो आपका बेड रहता है, उसमें जो आपकी रजाई होती है या क्विल्ट होती है जिसको कंफर्टर बोलते हैं, वो उसमें चिपकी रहती है. So it looks like his bed had the quilt, but Ramanujan didn't know how to use that quilt. So that is one of the very famous anecdotes about interactions of Mahalanobis and Ramanujan goes. So the topic I have chosen is about statistical thinking. There is a lot of discussion about the new area in computer science, in the interface of computer science and mathematics, which is called the data science. So if you look at data science, it is kind of an extension of a subject statistics, which has been there for a long time. Now, with the modern invent of these computers and all that, you can take the subject statistics to the next level. And that is how people have started using the word data science. Mostly used by the computer scientists, but traditional statisticians prefer to be covered by statistics, by a statistician, rather than a data scientist. So what I'm going to discuss about it is, my talk is going to be highly non-technical, right? So nothing complicated, very common sense. So I'm going to talk about statistical thinking. What is statistical thinking? No, as the name suggests, statistical thinking has to do something with the data because statistics has everything to do with the data. So my talk would emphasize on the fact that whenever you see a data, never trust the data at the face value. Try to develop a mindset where you go and try to read data of your own. Because data speaks a lot. If somebody else speaks on behalf of a data, that may not be exactly what is contained in the data. Like if you see these days newspapers, they're full of the second wave of COVID is going to come on second week of February. Somebody says, no, India, the COVID wave will not even come. No, you don't know what they're talking about, but they make great headlines, right? And they affect the society. So through this talk, I would like to motivate you that whenever you see a data, try to read the data of your own. And anybody can read a data in his own way, right? Data, because data speaks. The only difference may be possibly if you're trained in statistics with very sophisticated tools, you may be able to read a lot of things which are hidden in data. Somebody very naive may still be able to read something from the data, but not as much as any sophisticated statistician will do. So that's going to be the prime objective of this talk. Now, I would also explain the importance of reading through the data through some examples. That if you're not careful, you can read something very adverse from the data. And that is the whole purpose of this talk, to make you realize that you can speak with the data. once you're speaking with the data, and if you have a statistical mind, a statistical thinking, you can take out a lot from the data. Okay, so let me now formally start my talk. Yeah, so this talk is based on not a single source. The kind of things I have taken, they're standard stuff. You can find at multiple places, various textbooks, a lot of internet sites. There are multiple, and so of course, a lot of it has to do with my own personal experience with the subject. Now, if you see, if you call somebody illiterate, right? It's very insulting. If you call somebody illiterate, it's very insulting. But until a few years back or a few decades back, if you called somebody an innumerate means something who doesn't deals with numbers or doesn't deal with mathematics. It was fashionable to call that I'm innumerate. I don't know mathematics. I don't care about mathematics. Especially the people who are doing liberal arts. They consider themselves to be creative people, right? And they said the creative people don't have anything to do with mathematics. But those days are gone now. If you talk to your parents or grandparents, they would say, I'm not good at mathematics, so I'll do arts. So if you don't know any mathematics, you'll do arts. That means history, geography, civics, and those kind of subjects. If you're slightly better, you'll do a commerce, and you'll do science only if you're very good at mathematics. And somehow these all politics and everything was managed by people with background in arts. And that's how it became fashionable to say that, look, I'm not a numerate person. I'm enumerate, that's fine, that's fashionable. But those days are gone. For example, if you look at any very basic journal in economics, they do very sophisticated mathematics. Look at any journal in biosciences, any medical journal. They're full of all statistical studies and a lot of very sophisticated statistical methodologies and sophisticated mathematics. So the reason for discussing this was that it is very important that even if you don't love mathematics, try to make some love with the mathematics. Now let's look at what is statistical thinking. Now we are surrounded by, we are surrounded by complex systems throughout. In this COVID world, you must have realized that much more than any time before. What is going to happen, whether classes are going to be online, offline, hybrid mode, nobody knows. You all are depending on what some newspapers say or some mathematical people who do mathematical modeling are predicting. So we are surrounded by this very uncertain world throughout. And it's important to predict what's going to happen. The prediction may not be 100%, but if with certain confidence you can predict, for example, if with certain confidence, with 95% confidence, I can predict that third wave is not going to affect India. Or even if it is going to affect India, during what time period is it going to affect India? That's going to be very much useful for planning out things. So we are surrounded by complex systems that are difficult to understand and predict. Statistical thinking is nothing but understanding these complex systems phenomenon by capturing its prominent features through a limited sampling. So you have a limited knowledge about this whole complex system, which is, if I take the example of a COVID, in terms of how COVID has behaved in the first two waves. I also have data from the last epidemic, which happened 100 years back, 1970, Spanish flu. Now, based on that limited data, can I try to predict something about this complex system? because it is uncertain. What's going to happen 2 months from now, it's very difficult to predict. So statistical thinking is just to make some predictions about those complex systems based on the limited knowledge which you have about that complex system. And that is the primary goal of the subject statistics, if you look at. Now, one may say that in every sense, in the above sense, every human being or every living being is a statistician, because we all deal with the data. If you look at, for example, a totally illiterate Riksapular, right? Standing in a Choraha. He's doing very sophisticated mathematics, statistics in his mind, because he has a data from the past about the business he has been doing, about the money he has been making, what routes he has been following. So he's making predictions now, what route and what time I should take different routes so that I can make more money. So in subconscious mind, he's really doing some amount of sophisticated statistics. Then the natural question arises, doesn't that mean that statistics is nothing but just a common sense? You have a data, deal with it, and everybody is doing it in one way or the other. The answer is yes, everybody is doing statistics. There is no doubt about it. Even animals are dealing some amount of statistics in their own way. When tiger goes for his hunt, he's doing some statistics. The only difference is that trained statisticians do all this in a scientific manner. So there is well-developed statistical theory, and they follow that theory so that they can justify their decisions, why their decisions are the fair decisions. Somebody else who is not a trained statistician may still be doing a statistics, but he may not be able to provide justification for his decisions or his inferences which he may be drawing. So in a sense, statistical thinking is a way of thinking that is similar to that of a detective or an interrogator who is skeptical but has good scientific temperament while handling data. Right? So for example, if you must have heard the third degree, right? When when a suspect is caught, to get, suspect has certain amount of information, which I don't know. Now the job of interrogator is to get that information from him. A good interrogator will never use the third degree, right? Because if you use the third degree, something else other than the truth may come out. So a true statistician would be who has the data in front of him, and he can get the true picture from the data. And statistical thinking is all about that. Let me give how to start statistical thinking. Let me start with a simple example. Now, these producers have I have a habit of having a masala, like talak chai, right? You mix tea, milk, everything together, and then give me a tea. I like that kind of a tea. But if you go to Britain, they take tea, and if they like milk, they will take tea and milk separately. It's getting very common in India also these days. So tea and milk would be mixed up separately. Then there's a lady, this is an example of a real example in Cambridge. There's a lady who claims that just by tasting tea, she can determine whether tea was poured first or the milk was poured first. So she says that I have an ability, you offer me a tea, and I can tell you whether you poured the tea first or the milk first. Now that's a claim which this lady is making. Some people laugh at it. What difference does it make? Whether you pour tea first or the milk first, it's not going to make any difference. And people start suspecting this lady. But this lady is almost sure. So that's going to happen. You give me a tea and I'll do that. So now there is a claim which is to be tested. So what do? You design an experiment to test such a claim. So the issue is how to test the ability of lady to predict whether the tea or the milk was poured first. It is not possible to prove that C will never be wrong, because there is always a chance factor. After first 3 teas he has taken, possibly he was correct, and some other taste mixes with it, and there's a possibility that he might make an error. So there's always a chance that C may make an error. So in that sense, it is not possible to prove that C will never be wrong. To offer 100 teas, there is a high possibility that in one of the occasions or 2 of the occasions he will make a wrong judgment. So it will not be possible to prove that C will never be wrong. However, it is possible to disprove that C is never right. Right? You can always disprove that C is never right. Or that C is just guessing randomly. There is a possibility that C claims that I have such an ability, but C may be guessing randomly. So one can always test whether C is guessing randomly, or C actually can predict whether tea or the milk was poured first. Now, this is something which has to be tested. So as a statistician, what I'll do? I'll design an experiment for that lady and then draw the inferences. So let us see step by step what I'll do. Now, this designing of experiments is by R.F. Fisher, a famous British statistician. So what is being done is prepare 8 cups of tea. 4 tea poured first. In 4 of them, tea is poured first, and 4 of them, milk is poured first. And then you offer these 8 cups of tea to the lady in random order. She doesn't know which tea has been provided to her. That is being provided to her in a random order. So present these 8 cups to the lady in a random order and ask her to identify in which cups tea is poured first and which cups milk is poured. This is a very reasonable experiment to conduct because you're testing her claim. You observe certain data. So what you have done is, there is a random phenomenon which you don't know what the result is going to be. You conduct an experiment. Your experiment has given you a data. Now, based on the data obtained through above experiment, can it be proved that C was not guessing randomly? Or can it be proved that C has the ability to judge whether milk or tea was poured first with certain confidence? As I said, with 100% confidence, you cannot prove either way. No, so this is basically, so what you do is you design an experiment, you observe data, and based on the data you get, try to make decisions. And this is what whole the subject statistics is all about. And this is where the statistical thinking would come because data has come. Data speaks a lot about the ability of that lady to how to interpret that data. Data may be speaking a lot. Secondly, why only 8 cups? Are 8 cups enough? Why not 10 cups? Does it make difference? So then you have to see how this number of cups is related to the confidence you want to achieve. Right? You have more and more trials, more and more number of cups of tea for testing. Results are going to be much more precise. And then how to make inferences and estimate of how to give estimate of those confidence of your decisions. So this gives you a slight picture of how to think statistically, right, through an example. I've already talked about statistics as a subject. Now, this definition you might have seen many times is a branch of science that deals with decision making in situations involving uncertainty of outcomes of a process. Most of the process, in fact, that we come across in real life are random and exhibit uncertainty. It also deals with collection, summarization, analysis, interpretation, presentation, and organization of data. Once you have collected a data, how to present it, do you want to use all the information which is contained in the data? How to define information contained in the data? And so many other issues will come, which are technical in nature. Let me not touch upon it. Right now, what I'm emphasizing is data has a lot of information. You have to somehow structure that information for your use. And the final goal is drawing inferences about unpredictable phenomena or process that you're studying. For example, decision about whether to or not to replace the existing manufacturing process. There's already a manufacturing process. Somebody else comes up with the claim that, look, you employ my manufacturing process, this is going to be much more profitable to you. I am a factory manager or one who makes decisions about the factory. I'm faced with the problem whether to replace the existing manufacturing process by the new one or not. Certainly, for that, as I said, a way to address this problem is to conduct experiment, draw the data, and make your inferences about the data. And how to do all that would come through your formal training in the subject statistics. But what I'm trying to emphasize is that even if you're not trained in statistics, you can get a lot of information from the data. So let us go to this typical goal. If you're interested in studying certain characteristic of a population under study, say average height of a population of Indian male adults, average profit by an insurance agency using certain premium plan. For some reasons, I cannot get the data about the whole population. So what I do is I take a data only on a part of the population, which we call as a sample. Sample contains, which is your data, sample contains certain amount of information about the population. Based on this partial information about the population, you want to make inferences about the population. So that is what the whole goal is. So a representative of the population is chosen, and I said the sample contains only information about the population. Based on the information contained in the sample, statisticians make decision inferences about the populations. Now, statistics plays an important role in everyday life. So this all is about importance, I said. And then what is being conveyed through this few lines is that a formal training in statistics is important. But even if you don't have a formal training in statistics, try to develop a habit of reading through data. And that is what, as I have been emphasizing time and time again, is the purpose of this talk. Let me just skip this page. So this all talks about the importance of statistics. Once you have taken a data, summarizing a data is important. Removing the redundant data is important. Okay, now I'll give you examples of statistical thinking, just a common sense. And what you would see is through these examples, you'll get motivated to read through data. You might have seen a lot of reports. Sometimes you'll find a report that drinking alcohol is injurious to health, right? One day. Another magazine will come up with a study that drinking in moderation is good for health. Right? And all kind of funny studies you will come and you will believe that as if everything is true. Now, to understand that, whether that study is a legitimate study or not, you should try to see the data, what it is speaking. Along with the data, you should also try to see what are the assumptions he has made while making those predictions. So, for example, a lot of these COVID predictions are coming, and I find it very surprising to common man. When you predict something, he takes it at a face value. But all these forecasts or whatever predictions, one has to go into the validity of those assumptions which are being made. All use certain models. Certain models, when you're using, you make certain assumptions. Everything is hidden in those assumptions. If your assumptions are themselves non-practical, your final predictions are going to be non-practical. So let me give you example, let me explain you through examples how important it is to develop a statistical thinking, to speak to the data. Let us look at this example, which I'm calling this as a Simpson's paradox. And this says sometimes data in sight might lie. Data will never lie, but data in your sight might lie. So you should have a special sight, right, to get the correct picture of the data. So let us look at this example. This example is about admissions in UC Berkeley. University of California, Berkeley is one of the top schools. So there was a data about the admissions which were made in UC Berkeley. You look at men and women. There were 8,442 males, out of which 44% were admitted. There were 4,321 females, out of which only 35% were female. This is a real example. It's not a fake example. It's a real example. Now, when this data was published, people were furious, especially the female activists were furious that UC Berkeley is doing a discrimination. It is doing a discrimination in the sense that it is admitting only 35% of the female against 44% of that figure for male. So it is, in percentage, it is admitting lesser percentage of females than the male. And UC Berkeley was sued based on this figure. तो उनके अगेंस्ट मुकदमा हो गया यूसी बर्कले के साहब, आप तो लड़कियों के अगेंस्ट डिस्क्रिमिनेशन कर रहे हैं, आप लड़कियों को एडमिट नहीं करना चाहते. So data on sex-wise acceptance rates to admissions to different departments at the University of California for the academic year. UC Berkeley was sued for sex discrimination. Out of all the females that applied for admissions, only 35% were admitted, whereas out of all the male students who applied, 44% of them were admitted. Now, if you have to interpret this data, how will you do it? Now, your university, suppose you are a part of you're a dean of the UC Berkeley. How are you going to answer this? That, look, you are doing a sex discrimination, which is considered very serious. Any discrimination in US is considered to be very serious. So same thing happened. The dean of the university, who happened to be a statistician with the name P.J. Bickel, a famous statistician, he was approached. He said, look, we do a fair job. I don't know why it is happening. Why people are after us. He says, no, this data hides a lot of other things. What you see is not a real data. So you have to further uncover the data. This data, which is at your site, is telling you a lie. So this is the data in sight, that only 34% of females get admitted against 44% for the males. Then the Bickel said that give me the more data, give me the data department-wise. Let us look at what happens then. So the witch hunt was on to identify the culprits of gender discrimination. It said that find out who are the people responsible who are doing this kind of a discrimination. To do this, the data at the departmental level was analyzed so as to identify departments responsible for gender bias. So look at, I have just named them A, B, C, D, E, F. I have not written down the department's name actually. So department-wise data is over here. Now let us look at what is happening. 82%, 62%. Women were accepted more. 68%, 63%. Women were accepted more. 34%, 37%. So this here female were slightly less. 35%, 33%, again females were more. 24% and 28%. And then 7% and 6%. So out of these departments, in fact, four of them, females were accepted more than the males. So it said certainly there was a gender discrimination, but it was against males, not against females. Because 4 departments are favoring females. So you try to see what happens when you try to little bit uncover the data, the picture has changed. Now the question is, was there a discrimination? Yes and no. Why this is happening? The natural question arises, why this is happening? And you can easily see why it is happening. Just look at Department A. Department A acceptance rate for male and female is very high. Whereas very few female apply to Department A. What is happening to Department F? Acceptance rate is very low, but 341 females apply to Department F. You see, data is speaking a lot. You have to only get the real picture from the data why that was happening. You had original data, which was aggregated data. It was telling something else. The moment you try to cover it a little bit, you could find out what is the real reason. And what was the real reason? The real reason was that these females were applying to more competitive departments compared to men. So suddenly, if you apply to more competitive departments, selection is going to be much more tougher, and the acceptance rate is going to be lower. And that is what exactly happened over here. Now, this is called, in statistics, a Simpson's paradox, where these main effects get confounded. When you aggregate the data, your main effects get confounded. So all these minute details were getting mixed up when you aggregate the data. So notice that out of 6 departments, for 4 of the departments, acceptance rate for women was higher than that for men. This data tells altogether a different story, that there was certainly gender bias in admissions, but it was in favor of women and not against. Why did the aggregated data tell a different story? This is due to the confounding factor that is hidden within the data, as careful examination of the data would reveal, and that is what we have seen. Notice that Department A, which we saw just now, sorry, I thought I have. So notice that Department A has overall high acceptance rate, especially for females, but only 2.5% of all women applied to Department A. So very few females applied to Department A, where the acceptance rate was very high. And for men, this percentage was 9.77%. Of all the males, about 10% applied to Department A, which had a very high acceptance rate. And that is why more male were, male as well as, in terms of percentage, male and female were selected, but since very few female applied, in aggregate, it became very small. Further, Department F has overall very low acceptance rate for males as well as females. 7.89% of all women applied to this department. So a lot of females applied, roughly 8% of all the females applied to this very competitive department. And only 4.41% of men applied to this department. So what I'm trying to emphasize through this example is, which I have been emphasizing time and time again, that look, this data spoke a lot. And you have to read something from the data. So don't buy anything at the face value. So your studies like smoking is good or smoking is bad, or drinking is good, drinking is bad, drinking green tea is good or drinking green tea is bad. You should not take all those studies at face value. You should try to see those at the face value, try to see what study is talking about, what data is talking about. Now, this is called Simpson paradox, which arises in every area, business, medicine, and so on. There are a lot of examples. If you try to Google Simpson's paradox, you can come up with a lot of interesting examples, real-life examples. Okay. Now, there is a very simple mathematical explanation for this. Right? Anybody who tries to analyze it mathematically, for him, it would be a trivial job. What it says is A1 by B1 is less than C1 by D1. A2 by B2 is less than C2 by D2. Does not imply that A1 plus A2 upon B1 plus B2 would be less than C1 plus C2 upon D1 plus D2. So it is as simple as that mathematics. And that is what was happening when we were aggregating the data. Individually, department-wise, you saw that female, it was favoring female. But the moment you aggregated the data, the inequality changed. So, yeah, simple. So here I have illustrated in terms of example. 7 by 2 is less than 2 by 2. 1 by 2 is less than 5 by 8. But 7 plus 1 by 8 by 2 is bigger than 5 plus 2 by 2. Aggregated data will tell you a different story than the full data. Now then, let me take another example. So I've said I've tried to keep my talk technical so that you can understand the main motivation of the talk. Main motivation of the talk is don't take the data at the face value. Use your common sense to extract whatever is hidden in the data. It is also important to know what is there in the data and what is hidden in the data also. For example, the PJ Biggle did that. He said, no, this data is not enough. It is hiding a lot of things. So this accusation of that UC Berkeley does a sex discrimination, I'll not be able to tell unless I have seen more of a data which it is hiding. Now let's look at this example, another example which is about survivor bias. So you have to tell me when I have to stop. 5 minutes only? I think I will not be able to do fair because I thought 50 minutes, but then, okay, let me try to do that because I had prepared my talk keeping 50 minutes in mind, but that's okay. So this is about survivor bias. So in 1943, American warplanes were suffering serious damages from, so let me see. So I'll stop at 12:45, yeah? That's okay? Yeah? Huh? So 12:45, right? 10 minutes, you said, right? Okay. So in 1943, these American warplanes were suffering serious damages from German air defense, right? So all these planes were getting destroyed or getting damaged, these American warplanes. One way to handle the situation was to use more armor on planes, but they weigh a lot, that may affect their performance. So idea was to make them much stronger, put more, make them much stronger by putting a lot of other material and so on, but that may increase the weight, so that was not the solution. So the question is how much armor to use and where to use. That was the problem. So the Center for Naval Analysis had conducted a study of the damage done to aircraft that had returned from missions and had recommended that armor be added to the areas that showed the most damage. So this center suggested that, look, you already have a data. You already see the planes where the most damage, in what parts the most damage was done. Try to use the armor only in those areas where the maximum damage has taken place. Now, it's called a survivor bias. Now, then the issue was taken to a statistician, a famous statistician called Abraham Wald. I'll tell you something more about Abraham Wald. Abraham Wald said, look, I'm not happy with this data. You're only giving me the data of the warplanes which have returned back. What about the data about the warplanes which have not even returned back? And possibly they have not returned back because they have been hit in those areas where these people have not been hit. So if you hit in these areas, there is a chance of a survival. So the planes which have come back, they have survived. So that means those areas are stronger. So you have to put more armor in the areas which are complementary to this area because those are the planes which have not returned back. It's a simple thing, right? Once I tell you, it is a very simple thing. But what I'm saying is everything has to do with the statistical thing. It came to your mind, look, what is this data? This data is a very limited data. I cannot make any meaningful inference from this data. So I should also try to get the data for the planes which have not returned back. So Abraham Wald, who was at Columbia University, noted that the study only considered the aircraft that had survived their missions. The bombers that had been shot down were not present for the damage assessment. The holes in the returning aircraft then represented areas where a bomber could take damage and still return home safely. So that means उस area में मारो तो भी वापस आ गए. That means वो बाकी जो areas थे वहां पर मारा गया, वो गिर ही गया वहां पर plane, right? So they could never return back. So all proposed the Navy reinforce to Navy that they should reinforce areas where the returning aircraft were unscathed, since those were the areas that, if hit, would cause the plane to be lost. And this strategy turned out to be successful for Americans. Now, incidentally, this Wald died in India in one of the plane crashes. So Wild and his wife died in Air India plane crash, which happened in Nilgiri Mountains on December 13, 1950. So he was here to attend a meeting in ISI and then the Indian Science Congress meeting at Bangalore. And unfortunately, he died in one of those. Another example. This again has to do with the survivor bias, right? So a study carried out in 1987 revealed that cats falling from less than 6 stories and are still alive have greater injuries than cats who fall from higher than 6 stories. So there's a New York, you have a multi-storied buildings, and the Americans have a habit of having these cats as a pet. They are very popular. The windows, and then sometimes if window is open, they may fall. So the data revealed that all the cats who were falling from the 6 stories, from 6 stories or less, they had more injuries than the cats who were falling from the higher stories. So what was being proposed is that this might happen because cats reach terminal velocity after righting themselves at about 5 stories. So they say because they are falling from the top, they're falling. When they reach around 5 stories, they reach their terminal velocity, and then they are able to adjust themselves so that then when they fall, the injury is less. So that was the theory which was proposed, that look, those who are falling from the higher story, that could be a reason why this is happening. But in 2008, so there's a newspaper, Straight Dope, proposed that another possible explanation for this phenomenon would be survivorship bias, which happened in the case of planes also, right? That World War II. Cats that die in falls are less likely to be brought to a veterinary doctor. They fall and they must have died. They may not be even taken to the doctor, right? So there is a data which you have totally ignored over here. And this would come if you have a right kind of a statistical thinking. So you are like an interrogator. You say, look, no, you are telling only a part of a story. What is the other part of the story? So try to get whatever information you can get from the data. Almost, so this is another example about the hospital data. Let me just skip that. So Simpson's paradox, I would suggest that you try to Google Simpson's paradox. It will give you a lot of examples which deal with such a paradox. Mathematically, it's very simple in terms of probability. Those who know a little bit probability, it's very simple that probability of A given B less than probability of A given B prime may hold. This conditional probability may hold. But if you add another variable C, the inequality may change. So in the conditional probability, if you add along with B, C, this inequality may change. The way it was happening with those numbers example I took. So let me give you some tips about statistical thinking. So develop a habit of communicating with data and getting all the information it can provide. Equally important is to understand what information the given data does not provide. So what light is telling, whatever data is in your site, what light is telling. Learn modern statistical methods and latest computational techniques. Now, a lot of these softwares these days are available. Once you know statistical methods, there is a corresponding package available, and you can use that. Develop the habit of verifying the statistical theory through data and graphics. So you see, whenever you get such a study in the newspaper, develop it a habit that try to understand how they have concluded whatever they are saying. Once they are saying that second wave would come in the first week of February, what is the basis for making such a prediction? Try to understand. That will help you in developing this statistical thinking. In the process, develop a habit of making data speak You have to allow the data to speak. Try to statistically think about validity of conclusions of various studies reported in newspapers and magazines. Just briefly touch about challenges. You see, now what you do is a lot of computer scientists have started doing statistics. And they've started giving it a different name. They don't call it a statistics, they call it a data science. So a challenge with statistics as a subject is now the nature of the subject has to change, because earlier a lot of these methods were based assuming that a limited data would be available. But in the modern day, getting a data is not a problem. Right? You can get as much data as you want. So your methods have to be much more computer intensive. At the same time, the challenge with computer scientists is they also have to be well versed with various statistical methodologies, the statistical theories, and they have to verify whatever statistical methodology they are using, it has a good foundation. So that's a challenge for both statisticians and computer scientists. I'll give you one example. It's a very interesting example which I got through one of these WhatsApp messages, but very interesting and very relevant. So here's an elephant, which is a statistics. Here's a computer scientist like a python or a small snake. Snake approaches elephant. He says, we'll work together. He approaches further and says, please teach me some statistics. Now the elephant is gone, has taken a new form, and he says, now I am a data scientist. Right? So that's a good prediction of the challenges which I put forward. So let me stop over here. I think I have already taken 1 minute extra. Yeah, so let me just stop. I think no, I can take more questions. No problem. Yeah. So try to read it. The idea I see was very simple. The idea was not to make a talk which is very heavy. Idea is to just motivate you that try to start playing with the data. Whenever you see a data, develop a habit of being an interrogator and try to get a good information from that data. Data speaks a lot, let me tell you. Yeah. Okay. Jokes about that. Some people say that data scientist is somebody who knows more statistics than a computer scientist and less programming than a scientist, and vice versa. The computer scientists who know less statistics than more programming than. So yeah, to define it in a way. Nowadays it's very fascinating. Basically, the code is the same, but for both must be same. Except that now, computer scientists mostly don't prefer
Thank you, sir, for such a motivational talk. I hope the students present in the audience also get inclined towards statistics and its applications. Now we will have a lunch break up to 1:30 p.m. After lunch break, we will have some departmental activities followed by a quiz for participants. And after that, we will start the last invited talk by Professor Anupam Segai, Department of Mathematics, IIT Guwahati, from 3 p.m. Professor Segai will deliver his talk via online teleconferencing mode. I would now request all of you to move in silence to the basement for lunch. Mr. Pallav and Mr. Vinayak will guide you to the way to the basement.
So my slides are visible.
I would now like to introduce our next invited speaker, Professor Anupam Saikia. He is not present here due to some prior engagements at Guwahati, and he will deliver his speech through online teleconferencing mode. We are thankful to him for kindly accepting our invitation for today's talk. Professor Anupam Saikia is currently a professor in Department of Mathematics at IIT Guwahati. He has completed his PhD from University of Cambridge in the year 2001. His research interest broadly lies in the area of number theory. Professor Saikia has won several awards and scholarships during his career, including the Senior Roosevelt Fellowship and Ramanujan Fellowship to pursue his studies at Cambridge. He was a William Hodge Fellow at IHES Paris for a year. He is a member of editorial boards of Journal of Ramanujan Mathematical Society and the Bulletin of Mathematics Teacher Association India. The title of his today's talk is Number Theory and its Application. May I now request Professor Anupam Saikia for starting his talk.
Yeah, thank you for your kind introduction. And it's a great pleasure for an honor for me to deliver a talk on the occasion of National Mathematics Day, celebrated at IIT Bhilai. So today, I'll talk about number theory and its applications. So it will be a very basic talk, an introductory talk, and it is certainly for the non-experts. So what I plan to do in this talk is, because I was not sure about the composition of the audience, so I made it very elementary, and only towards the end we'll talk about elliptic curves and elliptic curve cryptography, because I want to talk about some applications. But to motivate the discussion on elliptic curves, I also will talk about a classical problem known as the congruent number problem. And even before that, I'll just give a very brief historical outline of number theory, but perhaps this audience is already familiar with all that. So yeah, so let me start with the historical outline, as I said. So as you know, the number theory is one of the oldest branches of mathematics, and it has to be, because mathematics starts with numbers. As soon as people started counting with 1, 2, 3, with natural numbers, so you can say that is the start of mathematics. So certainly this is the oldest branch. And its history, one can trace it back to Sumerians and Babylonians in Mesopotamia, which is like present-day Iraq. And then, of course, Egyptians, they also made contributions. And Greeks, whose names are, of course, familiar to us, like Pythagoras, Euclid, and Diophantus may be less familiar with those who are not exactly studying number theory, but certainly the other two names, like Pythagoras theorem, we all know in schools, and Euclidean geometry, all of us are familiar with. And Indians, of course, made significant contribution. I am just naming two, like Aryabhatta and Brahmagupta, but of course there are several others, like Madhava, Bhaskara, and others. And then you can say that modern number theory started with Fermat, which is, he is called the father of modern number theory. And as we know, Fermat was basically a lawyer in a provincial court in France, and he used to pursue mathematics as a hobby. And that way itself, he made very significant contributions. Like we all know Fermat's last theorem, although actually he did not prove it. It is like Fermat's last conjecture would have been more appropriate, that x to the power n plus y to the power n equal to z to the power n. It has no solutions for n bigger than 2 in integers, non-zero integers. So that was like an unsolved problem for 350 years. Of course, he could prove it for n equal to 4. He showed that x4 plus y4 equal to z4 has no solution. And his way of proof is also very interesting and is still relevant. That is known as Fermat's infinite descent. He showed that if one solution exists in positive integers, he'll have a smaller solution, and then he'll have a further smaller solution. But these positive integers, you cannot keep reducing. So that's why this he can rule out the solutions. Of course, other big names are like Euler, Legendre, Gauss, Dirichlet, and I'm sure students of mathematics are familiar with all these names. And this famous quotation of Gauss that mathematics is the queen of sciences and number theory is the queen of mathematics. And this is a quote that number theorists in particular like to refer to. And since on National Mathematics Day, since Ramanujan was also primarily, you can call him a number theorist. So we can make this quote here itself that Ramanujan worked on this queen of mathematics. Okay, and there's another famous quote by another great mathematician, Kronecker, that God created the natural numbers and all the rest is the work of man. Okay, so let's recall who are those men. And although looking at the audience, probably you all know this, that it is first we have to attribute to Pythagoras 600 BC and his followers, because they divided mathematics into 4 areas, major areas. They call it quadrivium. And this is like arithmetic, music, geometry, and astronomy, because even music, they considered it as a branch of mathematics. And then Euclid, of course, because Euclid's Elements, this is one of the most significant books ever in mathematics, because it was relevant even after thousands of years. It was written in around 300 BC, but it was relevant in 16th century, 17th century, or even now. So you can see, usually science books can get outdated, or scientific theory can get outdated. But these Elements, this is one of the most remarkable books. And it was written in 13 parts. Most volumes focus on geometry, but 3 volumes were devoted to number theory. And we'll get a glimpse of that. Like, for example, in Elements, Euclid showed that there are infinitely many primes. Okay. And his proof is quite elegant because it was a proof by contradiction. Probably you recall from your school days that you start with, let's say, E1 up to Pn, n primes. Then you take the product of all of them and add 1. Now what happens to this new number? It is not divisible by the previous primes. So either it is a new prime or it is divisible. If it is composite, then it will be divisible by some new prime, which is not one of those n that we started with. Okay, and there are many interesting questions from this question itself. Okay, like whether, like, say, suppose you start with 2 primes, 2 and 3. You multiply 2 and 3 and add 1, you get 7. Okay, it's a prime. And then 2, 3, and 5, you multiply and add 1, you get 31. That's a prime. The question is, do you get primes infinitely often? That question is still open. Or do you get infinitely many composite numbers? That is also open question. These kind of numbers are known as Euclidean numbers. Okay, so it shows that, okay, so that is one of the significant results, that there are infinitely many primes, very early results. Okay, but there's one very modern result. I mean, very modern meaning it is like 19th century, the Dirichlet's theorem on primes in arithmetic progression. That if you take any arithmetic progression, there should be infinitely many primes in it, unless you rule it out trivially. Trivially rule out meaning you take the first term and the common difference, which is not co-prime. Certainly, all the primes will, all the members will be composite. But if the first term and the common difference are co-prime, then in such a arithmetic progression, there will be infinitely many primes. That's what Dirichlet proved. And let's just see it through an example. Like you take 4 as the first term and 9 as the common difference. And you take the like arithmetic progression 4, 13, 22, 31, like that. Keep adding 9. And you find that these red colored ones are primes. And it is natural to ask whether there will be infinitely many. And the answer is yes. And the way Dirichlet answered it, that itself led to a lot of developments. Like he introduced the notion of Dirichlet L functions, which I'll not talk about, but I'll just roughly mention what the key idea is in this proof. That the idea of the proof is to show that the sum is infinite. What is that sum? You take the reciprocals of the primes appearing in such a arithmetic progression. But rather than just the reciprocals, to be more precise, you take the power s, you raise it to power s, and look at the sum as s approaches 1, whereas s is in fact a complex variable. Okay, and what you show is that this sum is infinite. Now, if you can show that this sum is infinite, certainly number of terms is infinite. Of course, if you have sum of infinitely many terms, it can be finite. That is also possible. Even a finite sum may have infinitely many terms, okay, like any convergent series. But certainly, if the sum is infinite or approaching infinity, certainly number of terms have to be infinite because individually each term is finite. So that's the way he proved it using, actually this is like almost like a Dirichlet L function. But since to introduce it more properly, it will require some time, and that is not the purpose of the talk, because the purpose is to give you a broad overview of number theory or some key results. And of course, these conjectures probably you all know, that I'm just mentioning, just to give you the impression that in number theory, it is very easy to relate to the statements, although they may be very difficult to prove, like Goldbach conjecture, that every even natural number n bigger than 4 can be written as sum of 2 primes. Like any even number you take, let's say 10, which is 7 plus 3, or 20, which is like 17 plus 3, you can say. So we can do that. But this statement is still unproven. You have billions of examples, but examples do not prove a theorem, as we know. So what people have tried? People have tried to prove weaker versions of this conjecture, like the weak Goldbach conjecture. Weak Goldbach conjecture, it says that every odd number greater than 5 can be expressed as the sum of 3 primes. Like take any odd number, let's say 11. You can write it as 5 plus 3 plus 3. Or 21, maybe it's 11 plus 7 plus 3. So that way you can write, you should be able to write any odd number as sum of 3 primes. And why it is called weak? Because the original Goldbach conjecture certainly implies this. Because if you have an odd number, you can subtract 3 and you can get an even number. Okay, like if 2n plus 1 is an odd number, you subtract 3. Then it is an even number, and by Goldbach conjecture, it should be sum of 2 primes. So you just shift 3 to the other side, and you get 2n plus 1 as 3 plus p plus q. And you can do so provided 2n plus 1 is bigger than, you need 2n plus 1 minus 3 bigger than 4, which is anyway odd numbers bigger than 5. So this is, but this statement people could make progress. The original Goldbach conjecture is, so to speak, like it is not easy to touch, but it's weak Goldbach conjecture. Several people contributed significantly. So I'll just mention a few key steps, like Terence Tao. Of course, you probably all know about Terence Tao, one of the most prominent mathematicians of our age, at the currently. And he actually showed that every odd integer is a sum of at most 5 primes. Okay, not quite the full conjecture, but at least at most 5 primes he did. Whereas, like much earlier, Vinogradov, he showed that all sufficiently large odd numbers can be expressed as sum of 3 primes. So this weak Goldbach, he could prove, but only after a point, after a finite point. So it may seem that, okay, now the conjecture is very easy because you have only finitely many cases to check. But unfortunately, Vinogradov's bound was too large. It was very large constant. And that constant itself was so huge that it was still a big task to show the conjecture for the smaller odd numbers, which was done eventually in 2013 by Helfgott. So we can now say that the weak Goldbach conjecture is proven. And in this context, since today is National Mathematics Day and Ramanujan is closely associated with Hardy, and Hardy and Littlewood also made significant contribution to this weak Goldbach conjecture. They also provided a proof, but that depended on Riemann hypothesis. Okay, so they assumed another hypothesis, which is still a conjecture. So that was a conditional proof only. Okay. Another famous conjecture you must have heard of is this twin prime conjecture, that there are infinitely many prime numbers such that p plus 2 is also a prime. For example, 3 and 5, 5 and 7, 11 and 13, that there are infinitely many primes. And this conjecture was also completely open for a long time. So I hope that my slides are visible. But let me know in case there is some problem. Okay. So this remained open for a long time till recent breakthrough. Okay. So that's why I want to mention. But before that, I also want to say that this was also generalized, that nothing special about 2. For every even integer 2n, there are infinitely many pairs of consecutive primes which differ by that even number. That is also a generalized conjecture. For example, what I mean by this, like if we take 6 as the even number, so you can see that 23 and 29, these are like consecutive primes with gap 6, or 31 and 37, 47 and 53. So these are like gap 6. So gap 6 also there should be infinitely many primes, just like gap 2, or for any even number. Okay. And what is that significant progress, recent progress after like 100 centuries, that Yitang Zhang in 2013, he proved that we may not know about gap of 2, but certainly we can show that there is a finite number B for which there will be infinitely many pairs of primes P and Q with the gap at most B. Meaning if we take, there will be infinitely many primes with gap at most B. And he proved it for 70 million. Okay. Whereas twin prime conjecture wants B to be 2. Basically, what is the twin prime conjecture? That there will be infinitely many pairs of primes where gap is bounded by 2. Gap bounded by 2 means gap should be 2, because if a prime number is odd, then certainly next number is even. So you cannot expect gap 1 certainly, except 2 and 3. You can never expect gap 2, gap 1, but certainly 2 is the best gap you can think of. Okay. And Zhang did it for 70 million. But after that, by a different method, Maynard showed in a simpler way that gap can be reduced to 600. And there has been a polymath project with Maynard, Terence Tao and Maynard and others, which they brought the bound down to 246 or something, and still I think it is coming down and down. Okay, but this is just to give an impression of the progress, recent progress of some big open questions. And the charm of number theory is that one can relate to these questions with school mathematics background. You don't need whereas probably to understand a problem in algebraic geometry or differentiable manifolds, you would require a lot of background even to appreciate what the problem is. Okay. So next, what I want to do is like another classical problem I want to mention, and also that problem motivates the study of elliptic curves. Okay, and so that's the congruent number problem. So before talking about congruent number problem, let me just define, okay, or what is the congruent number problem, how it is regarded. It is regarded as the oldest unresolved problem in number theory, or perhaps in the whole of mathematics, because it is older than the Fermat's last theorem, or Riemann hypothesis is much recent, so to speak, if you compare it to the congruent number problem. Okay, or the Goldbach conjecture, they are more recent. But this congruent number problem, its history can be traced back at least 1,000 years to an Arab manuscript. Okay. And nowadays, it can be thought of as a manifestation of a famous conjecture known as the Burs and Swinnerton-Dyer conjecture on elliptic curves. Okay. So this BSD conjecture, it is one of the 7 millennium problems. Okay. So you know that in the year 2000, 7 problems were identified for the mathematicians to focus on, just in the same spirit as Hilbert's 23 problems. In the year around 1900, Hilbert announced 23 problems for the mathematicians to work on in the next century. And those problems really stimulated the growth of mathematics in the 20th century. And some of those problems are still unsolved. So in the same spirit, in year 2000, 7 problems were identified, like P versus NP, or the BSD conjecture, Riemann hypothesis, and Poincaré's conjecture. And that was the only one which has been done. Okay, but others are open. Okay, so this is the congruent number problem. So what's that problem? Before that, I have to define what congruent numbers are. So let's denote the set of natural numbers by n and the rational numbers by q. A natural number n is called a congruent number if it occurs as the area of a right triangle. In other words, there should be some rational numbers. Right triangle with rational sides. Rational right triangle means you don't allow just any real number. You just allow rational numbers. Okay, since it's a right angle triangle, so a square plus b square should be c square. And n should be the area, so it is half times a times b should be n. So this type of numbers, natural numbers, they are called congruent numbers. For example, 6 is a congruent number. Why? Because we have 3 square plus 4 square is 5 square, and half into 3 into 4 is 6. Of course, here we have got integral sides, but we can in fact allow rational sides. Another interesting question is, if we have one such triangle, do we have infinitely many such triangles? And that answer is yes. That if we have one such triangle, then we can find infinitely many such triangles with n as area. And what is the congruent number problem? The problem of determining whether a given natural number is congruent or not. That is the congruent number problem. For example, like 1, 2, 3, 4, they are not congruent, but 5 is congruent. So similarly, any arbitrary number, if it is given to us, can we say whether it is congruent or not? And this a complete solution still remains elusive. Okay, so it is still, people have not been able to resolve it completely. So what people are doing is like reformulate the problem so that it can be handled in a better way. Okay, so how it is done? So a kind of reformulation which actually leads us to elliptic curves. So, and that curve, okay, I'll describe what an elliptic curve is. But first, suppose such a triangle exists, then we'll show that certain curve has a rational point. Okay, so suppose we have a right angle triangle. Okay, ABC it should have been, but AB, unfortunately, ABA is coming up on the screen. But C is the diagonal. Okay, so you keep the diagonal as C. And we want ABC to be non-zero rational numbers. It's a right triangle and area n. Okay, and it is easy to check that if we take x to be c by 2 whole square, then x plus minus n is also a rational square. It is like your old formula that a square plus b square minus 2ab is a plus b whole square, or a square plus b square minus 2ab is a minus b whole square. It is all that, that x plus minus n, they are all squares. But what it does is that now we can take x to be c by 2 whole square and y to be c times b minus a by 2 and b plus a by 2 and c by 2. So that you get basically c times b minus a, b plus a. Or I could have said a plus b and a minus b also. If we do that, then we find that y square is x cube minus n square x. In other words, from a rational triangle, we get a point x comma y on the curve y square equal to x cube minus n square x. What kind of point? It's a rational point. Why? Because a, b, c are rational numbers, so x and y are also rational. And converse is also true. Suppose I have a point x and y as rational numbers where y is non-zero, satisfying y square equal to x cube minus n square x, then we can take a to be x square minus n square by y, b to be 2xn by y, c to be x square plus n square by y. They will all be rational numbers and they'll satisfy a square plus b square equal to c square, and half of ab will be n. Okay, so in other words, existence of such a triangle of rational sides leads to a point on a curve with a non-zero y coordinate. Okay, so the question whether n is a congruent number reduces to the question of finding a rational point. Rational point meaning coordinates are rational with y coordinate non-zero on the curve y square equal to x cube minus n square x. Okay, and this type of curve, these are like they form a family of curves known as elliptic curves. And elliptic curves are slightly more general, but this kind of elliptic curve where we have this equation y square equal to x cube minus n square x, they are called congruent number elliptic curve. And a lot of progress has been made on congruent numbers using elliptic curve. So now we move to elliptic curves. So let's talk about these curves a little bit. What curves are these curves? Okay, what are these curves? And these curves also are quite classical in the sense that they appeared in the book Arithmetica by Diophantus in the 3rd century. Okay, and they have been used to prove Fermat's last theorem. Okay, and you probably know that it is one of the most significant development in number theory when Fermat's last theorem was proved by Andrew Wiles with the help of Richard Taylor in 1994. Okay, so the elliptic curve played a crucial role there, and of course in the congruent number problem, and this Barsan-Swedenborg-Dyer conjecture is also nothing but a relation between the algebraic properties of the curve and analytic properties of the curve. Okay, this algebraic side we'll see today. The analytic side, it is like an L function. Okay, so that I will not mention in this talk. But they elliptic curves are quite they are everywhere in many places. Okay, so is there some, okay, so I should show in the presentation mode. Okay, so just a moment, so shall I stop? Is it not sharing? Anurag, is it shared or not? Can you unmute and tell me? Is it better now? Okay, so I'm not sure.
Am I audible, sir?
Yeah.
Yeah, it is okay now. Yeah, thank you.
Okay, so I should have enlarged it, huh? Is it that?
Yeah.
Okay, I'm sorry
Thank
about
you.
that.
Yeah.
Okay, I'm sorry about that. Yeah, okay. So now, so elliptic curves, what are elliptic curves? Let me just quickly define that an elliptic curve over Q is a non-singular curve, and it is defined by an equation of the form y square equal to x cube plus ax plus b, where a and b are rational numbers. Okay, so there are a few things that in general elliptic curves have a more general form, but when the field has characteristic 0, certainly we can remove, I mean, like there's an x square term, for example, but that can be removed by shifting the origin. Similarly, there's an xy term which can be removed by like changing the coordinates. Okay, so that's why when a characteristic 0 field, certainly you can present the equation in this form. What does non-singularity mean? It means there is a well-defined tangent at each of its points. Okay, non-singular means it has a well-defined tangent at each point. For example, if I take this curve y square equal to x square times x plus 1, then certainly at the origin you can see that there are two tangents, or in fact there is no well-defined tangent. It's like a node. What it is called a node, and this next one it is called a cusp. Okay, it's a node and cusp. So this type of situation you don't want. If you don't have this, if you have a well-defined direction at each point of the curve, then it is called a non-singular curve. And you can see that this is just a generalization from your classical conic sections. In classical conic sections, you have you have a quadratic equation in x and y, but here this equation in x can be cubic. Okay, that is a major difference from classical conic sections to elliptic curves. Okay, and elliptic curves enjoy many special properties that we will mention. But one thing to be noted is like this cubic curve is very significant. Okay, if you take a very high degree, when you get hyperelliptic curves, then they lose many of these properties. Okay, so let's see what is special about elliptic curve, that they have a group structure. If you take points on an elliptic curve, then we can add the points. 2 points I can add and I can get a third point in such a way that the operations have identity, inverse, associativity, and commutativity. So in other words, the points on an elliptic curve form an abelian group. Okay? And I'll just briefly mention how this group structure works. And for that, it is most convenient to take a point at infinity. Okay. So what is that point at infinity? Okay, you take all the points that satisfy y square equal to x cube plus ax plus b, and you take a point at infinity, meaning y coordinate is infinite. X coordinate can be anything. Okay. So that is the notion of infinity, point at infinity. And this addition is explained by this chord and tangent method. Okay. Suppose this is the elliptic curve, y square is x cube plus ax plus b. Suppose I have 2 points, x1, y1, which is P, and x2, y2, which I'm calling Q. So how do we add these 2 points and get a third point? We join them by a straight line, y equal to mx plus c. And if I substitute in y square equal to x cube plus ax plus b, this is a cubic equation, so we'll be having 3 roots. But 2 of the roots are already known, like x1 and x2 are roots. So I get the third root, which is x3, which is m square minus x1 minus x2. Okay, so once I get the x coordinate, I also get the y coordinate from this equation, y equal to mx plus c. And further, one can note that if x1, y1 and x2, y2 are rational numbers, then the slope is also rational and y-intercept is also rational. In other words, x3 will be rational and y3 will be rational. So by adding rational points, we'll get rational points. Okay. But this, so that point we denote by P star Q. But this point itself, we don't call it P plus Q because we want an identity for this operation. We want an inverse, etc. For that, we have to involve the point at infinity. So to get P plus Q, we just reflect along the x-axis, or you can say you draw a vertical line through P star Q, and again it will hit the curve at a third point, and that will be called the sum of P and Q. And one can check that in this process, this point at infinity is the identity for the operation, and like inverse is like the reflection along the x-axis, etc. Okay, so all this can be checked, but which we will not do because we just want to give a brief impression how this group law works, that how we add points. Basically, you have to draw 2 chords, one through P and Q, and then one with the point at infinity and the third point of intersection. And in this process, we get associativity, commutativity. Commutativity is obvious, most obvious, because joining a line P and Q, or whether you are joining Q and P, certainly it is the same straight line. So clearly P plus Q equal to Q plus P, that is the most obvious among these properties. Okay. And this is working because it's a cubic equation. So that's why like you have a third root. Okay, so this cubic thing is important. And you may wonder, like sometimes you may not get the third root. Okay, so you may not see the intersection. So we'll have to interpret as like these points may be over the complex numbers also. Okay, so there are other ways to things to be considered, which of course we will not do in full detail. And why do we want a non-singular curve? Because what happens if I want to add P to itself? Because I should be able to add P to itself. That is like Q is coming closer and closer to P. So basically you are getting the tangent. You have to use the tangent at P. And that's why you need a well-defined tangent at each point. That's why the curve should be non-singular for this group structure to work. That if you want to add P to itself, you just draw the tangent and do the rest as before. The tangent also will hit it at the third point, and then you join it with the point of infinity, and you get P plus P. Okay. And once you can add a point to itself, you can multiply by any integer. Like if I take any integer, let's say 10, I can add P 10 times, I'll get 10P. Or if I multiply by minus 10, what I will do, I'll take minus p and 8 10 times. What is minus p? It is the inverse. It is the inverse of p. In fact, it is the reflection of p along the x-axis. And in this process, if it happens that this point has finite order, meaning if after multiplication by some n, if we get the identity element, then we call it a torsion point. It's like in a group, so, it's a point of finite order, an element of finite order, that's like a torsion point. And there might be points of infinite order also. And there's this group of all the rational points on the elliptic curve. It is called the model wheel group. Okay, what is the model wheel group for an elliptic curve E? You take all the points x and y in Q such that they satisfy the equation, and of course together with this point at infinity. Okay, then this is a group, and this famous model wheel theorem is that it's a finitely generated abelian group. It's an abelian group, that is easy to see. Important thing is it is finitely generated, and if you are not familiar with finitely generated abelian group, you can say it is the analog of finite dimensional vector space. In a finite dimensional vector space, you just need finitely many vectors, and all the other vectors you can get as linear combinations. Similarly, this group EQ, there will be a finite set of points. If you keep adding them among themselves, you'll get the whole group. And so this group can be written as some copies of Z plus a finite part. Those who are familiar with the structure theorem of finitely generated abelian groups, this is quite clear. For others, this is like this RE, it is like the number of copies of Z. This is known as the rank of E over Q. It is like the analog of dimension of a vector space. Okay, this is like the correspond to the points of infinite order. If there is one point of infinite order, and of course it's multiples. So if there is one point of infinite order, then rank is 1. If you have 3 points of infinite order which are not dependent, which cannot be, one cannot be expressed in terms of the other two, meaning one should not be like 10 times the first one and plus 20 times the second one. Okay, so in other words, they should be independent points, then the rank will be 3. And this BSD conjecture is a statement about this rank. Okay, and there are many open questions concerning the rank. Computing the rank of an elliptic curve is a very hard problem. Whereas this torsion part is easy. This finite part is easily understood. I'll just mention a few results, like the Lutz-Nagel theorem, that a torsion point has integral coordinates. Okay, even if you're considering rational points, but in fact, a torsion point has integral coordinates. So it is easy to find. And even if you change the elliptic curve, there are only 15 possibilities for this finite part. This is a very big theorem of Mazur, that whatever elliptic curve you take, the finite part, these points of finite order, they will form a group which can be only one of the 15 given by Mazur. Okay, and then people try to find analog over other number fields, meaning finite extensions of Q, but finding the rank is very difficult, and it is not even known whether the rank can be arbitrarily large. So far, only example known is up to 28. Highest possible rank known is like 28. But in theory, no one has ruled out that rank is bounded by whatever. You may change the elliptic curve, that rank will be bounded by some number, or that rank will not be bounded. That kind of result is not there. And this first part of BSD conjecture, which is a $1 million question, that is, I mean, literally $1 million question, because these Millennium Problems has a 1 million price tag also. It relates the rank of an elliptic curve to the L function of the elliptic curve. Okay. It says basically the rank equals the order of vanishing of the L function at s equal to 1. Okay, but we will not go further into those details. But let's see how it relates to the congruent number problem. Okay, so what progress has been made on the congruent number problem using elliptic curve? Okay, so we know that a point on the congruent number elliptic curve with y coordinate non-zero is of infinite order. Okay, so So the congruent number elliptic curve, we need a point of infinite order so that n appears as the area of a right triangle. Because if y is 0, then that point has order in fact 2. Okay? And there are no other torsion points. So whether n is a congruent number or not, it is equivalent to saying whether the elliptic curve has infinitely many rational points. Okay, so n is a congruent number if and only if the elliptic curve has infinitely many rational points. Okay, now people could work something out of this. For example, Nagel showed that if you take a prime of the form 8k plus 3, then E and Q has to be finite, and hence such primes are non-congruent. Like for example, you take 3, then x cube minus 3 square x, okay, y square equal to x cube minus 3 square x. This has only finitely many points. That's what Nagel showed, and hence 3 has to be a non-congruent. Okay, and this BSD conjecture, through L function, it predicts that any number which is of the form 8k plus 5, 8k plus 6, or 8k plus 7, they should be congruent. Like 5, 6, 7, they themselves are congruent. And similarly, 8 plus 5, 13 should be congruent, etc. But this is just a prediction because the conjecture itself is unproven. Okay. And then Higner, that's another significant piece of work. He showed that you take a prime of the form 8k plus 3 and you take twice that prime, then that elliptic curve has a point of infinite order, meaning a point where y coordinate is non-zero, and hence that kind of twice that prime is a congruent number. For example, 2 times 3, 6 is a congruent number, and 11. So if you take k equal to 1, so 22 should be a congruent number. Should be normally, it is a congruent number. So, and Monsky, that's another significant development. He used this method. He extended Higner's method, and he showed it for primes of the form 8k plus 5 or 8k plus 7. Okay. And Tian also made significant generalization. So this is the progress on congruent number problem via elliptic curves. So finally, I'll talk about some practical applications, because as students of mathematics or people involved in mathematics, we are often asked, what is the point that you are doing and what is its application? How does it matter in real life that this theory of elliptic curves or any other numbers, how they are applicable? That this one application is this elliptic curve cryptography. And those who are unfamiliar with cryptography, you can say that even the hieroglyphs of Egypt, they are nothing but a form of cryptography. Okay? Because it's like hidden writing. So cryptography, the word is coined by joining two Greek words, crypto and graphene. Crypto means hidden and graphene means writing. So it's hidden writing. And it was there in very like thousands of years earlier, like Julius Caesar's time. Okay. And it was very much needed because suppose the king wants to pass some order to the general, then he doesn't want this message to be known by others. So that kind of secrecy was required. And a very primitive form of cryptography was used. Like you shift the letters by 3. Like in place of A, you write D. In place of B, you write E. So that is the way you code the message. And then recipient can just go back 3 letters and recover the message. But as you can see, it is very crude. And probably it worked thousands of years ago. But certainly it is not going to work at present. So you need better tools, which was provided first by Rivest, Shamir, and Edelman. That is the RSA crypto system. But that RSA crypto system also has certain limitations. And another crypto system evolved using elliptic curves. And it was proposed separately by Neil Koblitz and Victor Miller. Okay, they independently developed this. And overall, you can say, roughly speaking, it is more efficient and secure. Okay, more efficient in terms of memory and all. Okay, and security also is like you can say that is more efficient basically. So let me just give the broad idea, like what is used in this crypto system. Okay, so it is based on the discrete log problem. So we all know that discrete log problem is what? That if we are given a real number and a natural number n, then we can quickly compute x to the power n. Suppose we are given a real number x and a natural number n. Quickly you can compute x to the power n, y equal to x to the power n. But if we are given only y and x and we have to find n, in other words, if we want to find log y to the base x, it is much harder. Let me just illustrate. Suppose I want to compute x to the power 17. I don't need 16 multiplications. I need only 5 multiplications, because I will do like I'll square it, that is 1 multiplication. Then I'll square it, that is 2 multiplication. Then I will do another squaring, which is 3 multiplications, another squaring, 4 multiplications. I'm getting x to the power 16 and I multiply with x. So I get with 5 multiplications, I get x to the power 17. So I can skip steps. I don't need x to the power 7 or x to the power 11 or 13. So I could skip. But whereas, suppose I am given x to the power 17 as y and x. Now I cannot skip, because it is possible that x could be x to the power 11 or x to the power 13. So I have to compute all these powers. Okay, so in other words, I'll have to do 16 multiplications, which will be more time consuming. Okay, so that is the idea that is used. Of course, these computations are done modulo some number. Okay, so that even from the size, you cannot just say that this one is big, this is cannot be 5 or 7. Okay, because it will be actually you'll be doing modulo some integer. So, but this is just the idea. Okay, so this problem is the discrete log problem. And elliptic curve also gives this kind of discrete log problem. It is known as ECDLP, elliptic curve discrete log problem. Suppose we are given a point P on the elliptic curve and an integer n, we can easily compute n times P. Already we showed that how to double points with the tangent. And similarly, we can keep adding like 2P, 2P, then I get 3P, etc. So I get NP. But if you are given NP and P, it is difficult to find n, just like the discrete log problem. So this is the elliptic curve discrete log problem. And since it is crucial to us, let me just illustrate. Suppose I have a point P, and suppose I have an integer, say 233. And suppose we want 233 times P. Then we don't need 233 additions. We just need very few additions. Like 233 we'll write in the base 2. Then we'll see that we can get this as 2 to the power 7p plus 2 to the power 6p plus 2 to the power 5p plus 2 cube p plus p. So you can see that basically you need only 11 additions, because this is like 3 additions, and then you have like 2 more additions. Okay, and similarly you have very few additions. Okay, with very few additions it can be managed. So you are saving, you are not adding 232 times, and that provides the security, so to speak. Okay, because we will skip a lot of steps. Okay, so let's see how we exploit this. Okay, how we exploit. For that, let's take an elliptic curve over a finite field. We have only defined over rational numbers, but just analogously, we can do it over any base field. We can take real numbers, complex numbers, finite fields like Z mod 5Z or Z mod 11Z. In fact, it will be like Z modulo some big prime. Okay, so it will be basically of the form Z mod PZ for some big prime. So take an elliptic curve over a finite field, and we fix a point on that curve, which is known to all. Okay, fix that point. And you can choose any random integer as secret key. So typically in cryptography, there are 2 persons. One person is called Alice and the other person is known as Bob. And it's like Alice wants to send some message to Bob. So it's a standard way of writing. So I'm also using Alice and Bob, or we can just say A and B. Suppose A wants to send a message to B, which should not be read by others. So she chooses a secret key, and the intended receiver, he chooses a random integer B as a secret key. Okay, they are kept secret, But what they publicly announce is A times the base point and B times the base point. AT and BT, they are publicly known. Okay. And the intention is that anyone can send messages to them, but only they should be able to decipher. So how the message gets hidden? Suppose Alice wants to send a message, that message is encoded as a point on the elliptic curve. It can be the x coordinate. Okay, it can be the x coordinate, typically x coordinate of the point. Okay, because you have an elliptic curve, and suppose you have some message in letters. Letters can be easily converted to numbers. For example, a crude way would be like convert A to 01, B to 02, and C to 03, like that. So even easy way of converting letters to numbers. Okay, and that number itself need not be a square after you take x cube plus ax plus b, but you can adjust it. You can always throw in some extra letters so that it becomes, it gives a point x comma y on the elliptic curve. Okay, that can be adjusted. So you can say that the message is the x coordinate of the point P. Now, this encryption will be like this, that P plus A times BT. So BT is publicly known. So Alice also knows what BT is, and she has her secret key A. Okay, so she will send P plus A times BT to Bob. Okay, now Bob should be able to recover this. So how will Bob recover? Because Bob receives P plus A times BT. Okay, he does not know A, but he knows A times T. Okay, A times T is publicly declared. So he will multiply with his secret key B. And A times BT is same as B times AT, right? Because I mean, this is an abelian group and all, and so A times BT is B times AT. Okay, so what he'll do, he'll subtract from P plus ABT this BAT, and he'll recover P. So he will subtract B times AT from P plus A times BT, so that only P he'll be able to extract. What will an eavesdropper do? Okay, eavesdropper will find it very difficult because he will know AT and BT. He'll know BT, but he'll not be able to know B unless he solves the discrete log problem. And that discrete log problem, solving the discrete log problem will take too much time. That you know T and BT, but you don't know B. So that is like the discrete log problem. So that's how the message is hidden. Okay. So this is very, it takes a lot of time. So that is the idea of the this encryption and decryption. So yeah, that is roughly what so let me just summarize what we did. Apart from this historical outline, I talked about this congruent number problem, meaning natural numbers which can appear as the area of a right angle triangle with rational sides. And that is an unsolved problem. But reformulation of the problem leads to an elliptic curve, y square equal to x cube minus n square x. If that curve has a rational point with non-zero y coordinate, it is equivalent to saying n is congruent. But what is special about a point on the curve with non-zero y coordinate? That's a point of infinite order, meaning the corresponding elliptic curve should have infinitely many points. Okay. And then people have made progress by ruling out infinitely many solutions to show non-congruent number, or they show that there are like infinitely many solutions, then n is a congruent number. So that's the way they do it. And finally, how it is useful in practical life, that it is used in encrypting and decrypting messages, or in cryptography. Like you can convert the message into the x coordinate of a given elliptic curve with a base point. And then you can send messages secretly, and then it is very difficult to break because of the discrete log problem. What is the discrete log problem? Like if you have like n and p, you can quickly compute NP by skipping steps. You can go in powers of 2, whereas the converse problem, it's like a trapdoor problem. Okay, you cannot, like if you are given NP and P, you cannot find n easily. You have to check whether 2p is np or 3p is np. That way you have to calculate a lot. Okay, so that's roughly what I wanted to say. And of course, if you're interested, then like in elliptic curves, like these are like this Koblitz, who is one of the guys who invented elliptic curve cryptography. He has also written a nice book on elliptic curves and modular forms and deals with a congruent number problem. Okay, this book is on elliptic curves, but geared towards the congruent number problem. And of course, there are many articles, nice articles like the ones by John Coates and Kate Conrad. And of course, the books that everyone follows for elliptic curve, the first one is like Rational Points on Elliptic Curves by Silverman and Tate. And the next level book is Arithmetic of Elliptic Curves by Silverman. So I'd like to thank you all for your attention. And if you have any question, I would try to answer. But let me thank the organizers for this invitation. And I really appreciate their effort in organizing this National Mathematics Day. Certainly, it's a very good initiative. And that is the right way to show our respect to this unparalleled genius and mystery, such a mysterious person, in the sense that like it is still no one could see how he obtained those results and how it came to do. I mean, how those results came to his mind is really mind-boggling. And even Hardy or other contemporary mathematicians, they were astounded by Ramanujan's genius, that how he could hit upon these results without kind of knowing how to prove them, but he could already sense what is the truth, or he could extract these deep truths, mathematical truths. So this is really really mysterious, and that's why like even now, like people hold him in very high regard, in awe of him. Okay? And you know that how he was like regarded by Hardy, like he was, I think, assigning 28 marks out of 100 to Hilbert, who is a very influential mathematician, but he like gave 100 out of 100 for, that's like an anecdote, okay, so probably true. But anyway, so yeah, it's certainly you can be proud of such a, that he was like an Indian mathematician. And yeah, so thank you all for your attention.
Hello. Thank you, Professor Sekia.
Thank you.
It's really, we are grateful that you have spared so much time from your busy schedule and gave a very nice lecture, particularly fruitful to the students of class 11, 12th, even the students who are interested in doing the cryptography, working in their side. I really appreciate the topic which you have chosen, particularly for this day. Thank you once again. And before I leave, I would like to introduce our other two speakers who have also given a lot of time, as well as they have chosen the topics which are very much beneficial and related to this mathematics day. One of them, Sir Punnuswamy, is here with me. He is from IIT Chennai, and others are. क्या हुआ? Oh, camera is not visible. So it is. It's okay. And Professor Neeraj Mishra from IIT Kanpur, in a very informative and useful talk on the statistic thinking of them. Particularly the person like me who is not at all knowing about the statistics and probability, I got interest at his lectures. So, Professor, once again, I thanks on behalf of the IIT Bhilai and on my own behalf, as well as from my own faculty members and others, appreciate all three of you for contributing your valuable lectures to us. Okay, thank you very much.
Thanks.
Thank you, sir, for such an interesting talk. I hope your lecture motivated the students present in the audience to study number theory, as it has numerous interesting applications. Now I request Dr. Kuldeep Kumar Kataria for prize distribution session.
Thank you, Shivani. So I hope all of you enjoyed the quiz. Yes or no? Okay. So see, winning and losing is a part of the game, right? But the most important thing I believe is the active participation, and you all actively participated with, full josh. Okay. So now I would request our invited speaker, Professor S. Pannuswamy, Professor Neeraj Mishra, and the head of the Department of Mathematics, Professor P.D. Srivastava, to please come on the dais for prize distribution. So we will start by giving the participation certificates first. Okay. So first I would like to invite team 1, which is Government Nagarjun PG College of Science, Raipur. So all the students, please come on the dais. Just okay, thank you. Now I would like to invite team 8, Government VYT PG Autonomous College. So all the students, please come on the dais. Thank you. Okay. Now I would like to invite team 2, Seth Fulchand Agarwal Smriti Mahavidyalaya. So students, please come on the dais. Thank you. Now I would like to invite team 4 from Krishna Public School. Yes, a student of Krishna Public School. Okay, so now I would like to invite team 7, from Bhilai Institute of Technology, Durg. Okay, so thank you. Now we will go to the winning teams. So first I would like to invite the team 6. Okay, so from Department of Mathematics IT Bhilai, who has secured third position in this quiz. So all the members of team 3. So may I request Professor Srivastava to please. Thank you. Now I request Professor Neeraj Mishra to give away the second prize to Center of Basic Science, that is team 3, from Pandit Ravi Shankar Shukla University, Raipur. Thank you. So now I request Professor S. Ponnuswamy to give away the winner trophy. Okay, so the winning team is team 5, that is from School of Studies in Mathematics, Pandit Ravi Shankar Shukla University, Raipur. Students, please come on the dais. A big round of applause to all of them. Thank you, sir. So congratulations once again to all the winners and participants.
Thank you, sir. Now I would like to invite Dr. Pawan Kumar Mishra, Assistant Professor in Department of Mathematics, IIT Bhilai, for giving vote of thanks.
So, a very good evening to all of you. It is my privilege to take this opportunity to deliver a vote of thanks on this auspicious occasion of birth anniversary of the great Indian mathematician Srinivasa Ramanujan. I, on behalf of the organizing committee, extend a very heartful vote of thanks to the invited speakers, Professor S. Punaswamy, Professor Neeraj Misra, Professor Anupam Saikia, who enlightened us with their insightful talks and of course took out their valuable time from their busy schedule on this occasion of National Mathematics Day. We had an opportunity to hear your motivational and inspiring talks, and I'm pretty sure that this will encourage the young brains to excel in the mathematics and the related areas. I would like to extend a special thanks to Professor Rajat Muna, Director IT Bhilai, for gracing this occasion and sparing time from his extremely tight schedule. I would also express my gratitude to him for his words of wisdom in the welcome address. With a deep sense of appreciation, I thank our head of the department, Professor P.D. Srivastava, for guiding and stimulating us to organize this event. I thank all the participants offline or online for their support and active participation in this event. As no program can become successful without a teamwork, we are very thankful and fortunate enough to be backed by very proactive and dedicated staff. At last, I would like to congratulate the Department of Mathematics, especially the students who participated actively to make this event a success. Thanks again to each and everyone who is directly or indirectly involved in this event and making this event a success. So I would like to make a small announcement. We will have a photo session before tea, and after photo session, we will have a tea break. Okay. It will be here on in this room itself. Thank you.